Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into Earth's first atmosphere, when the sky was held up by geological giants and the planet learned to breathe. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. 4.5 billion years ago, there is no sky to speak of. The Hadean Earth spins beneath a thin veil of hydrogen and helium, gases so light they drift away into space like whispered secrets. The planet's surface glows molten orange, a sea of liquid rock that stretches from horizon to horizon. No mountains yet pierce this burning ocean. No continents provide anchor points for weather systems. The world breathes in the most primitive way possible through countless volcanic vents that puncture the liquid stone, releasing the first substantial exhalations of what will become our atmosphere. Water vapor rises in slow, invisible columns from these wounds in the Earth's skin. Each molecule of H2O carries the heat of the planet's core, ascending through the thin air like thermal prayers. Carbon dioxide bubbles up from the depths, released from dissolved carbonates and organic compounds buried in the primordial magma. The CO2 emerges in concentrations that dwarf anything modern Earth has known, perhaps 1,000 times more abundant than today's trace amounts. Sulfur compounds paint the emerging sky in shades of amber and rust, while nitrogen begins its patient accumulation, molecule by molecule, breath by breath. The early atmosphere weighs almost nothing, perhaps 1% of its modern density. A human transported to this time would find no breathable air, no protective ozone layer, no familiar blue dome overhead. Instead, they would witness something far more alien: the slow birth of aerial space itself. The boundary between stone and void grows thicker with each volcanic pulse, yet remains so tenuous that cosmic radiation penetrates freely to the surface below. Each volcanic fountain operates on its own geological timeline. Some vents exhale steadily for thousands of years, building localized domes of gas that drift and merge with neighboring exhalations. Others burst in episodic releases, adding sudden clouds of vapor to the gradually thickening envelope. The volcanic gases carry trace elements that will not be understood for billions of years: rare earth metals, noble gases, isotopic signatures that future geologists will read like ancient texts written in atomic ink. The planet demonstrates its capacity for patience. What began as simple outgassing will require another billion years to stabilize into something resembling a modern atmosphere. The volcanic fountains show no urgency, no haste. They simply continue their work, breath by breath, building the foundation for a sky that does not yet know it will one day hold clouds. Only took 4.5 billion years to get the recipe right, and even now, the atmosphere continues its slow evolution, adding and subtracting molecules with each passing millennium. The temperature of these early exhalations reaches extremes that would sterilize any modern ecosystem. Volcanic gases emerge at temperatures exceeding 1,000 degrees Celsius, yet they cool rapidly in the thin air, condensing into droplets that fall back to the molten surface like rain returning to its source. This earliest water cycle operates without oceans, without land, without any stable reservoirs, just an endless circulation between liquid stone and gaseous space. Scientists remain uncertain whether this early atmosphere could have supported any greenhouse warming, given how thin it was. Computer models suggest that even with high concentrations of carbon dioxide, the atmosphere lacked the density necessary to trap significant heat. The molecular dance between gas and gravity had barely begun. Solar radiation penetrated freely to the surface, while the planet's own thermal radiation escaped just as easily back to space, the greenhouse effect. That gentle blanket of atmospheric warming that will eventually make life possible remained centuries away from its first tentative embrace. Yet already, subtle patterns emerge in the chaos. Convection cells begin to form as hot gases rise and cooler gases descend. The planet's rotation starts to influence these movements, creating the first hints of atmospheric circulation. These early currents carry volcanic gases across vast distances, distributing the chemical foundations of future weather systems around the globe. What looks like random turbulence actually follows physical laws that will govern atmospheric dynamics for eons to come. The boundary between day and night becomes more pronounced as atmospheric density increases. During the long Hadean day, perhaps only 6 hours from sunrise to sunset, due to the planet's rapid rotation, thermal currents rise more vigorously. At night, the thin air cools quickly, and gases settle toward the surface in gentle, invisible waterfalls of molecular descent. This diurnal breathing becomes Earth's first rhythm, a planetary heartbeat measured in temperature gradients and pressure changes. Deep in the volcanic vents, geochemical processes create molecular combinations that will prove crucial for future life. Hydrogen sulfide mixes with water vapor to form compounds that primitive bacteria will one day metabolize. Carbon monoxide emerges alongside carbon dioxide, providing potential energy sources for chemosynthetic organisms still millions of years in the future. The atmosphere begins to function as a vast chemical reactor, mixing elements and compounds in combinations that purely geological processes could never achieve. The persistence of stone, breathing fire into emptiness, promises something more substantial to come. Each volcanic pulse adds not just gases, but also fine particles of ash and dust that will eventually settle to form the first sedimentary layers. These airborne minerals catch and scatter the young sun's light, creating the earliest sunsets, probably deep reds and oranges painted across a sky that holds neither birds nor insects, neither seeds nor spores. Nothing but the slow circulation of heated gases above a world still learning the difference between solid and void. Only the patient accumulation of molecular breath by molecular breath suggests that this seemingly barren envelope will one day cradle forests, support migration routes for countless species, and provide the medium through which whale songs travel across ocean basins. The Hadean atmosphere knows none of this future complexity. It simply continues its fundamental task, transforming volcanic exhalation into the foundational layer of all future skies. The weight of ancient air begins to accumulate like sediment in reverse, building upward from the molten surface in layers of increasing complexity. As volcanic outgassing continues its patient work, the early atmosphere discovers gravity's gentle but inexorable sorting mechanism. Heavier gases sink toward the warming Earth while lighter molecules drift upward, creating the first primitive stratification that will eventually become the familiar layers of troposphere, stratosphere, and beyond. Carbon dioxide, with its molecular weight nearly twice that of nitrogen, settles into the lower reaches of this growing envelope. Each CO2 molecule carries 44 atomic mass units compared to nitrogen's 28, a difference that seems trivial until multiplied across billions of tons of atmospheric gas. This slight weight advantage allows carbon dioxide to dominate the surface air, creating concentrations perhaps 1,000 times greater than those found in modern Earth's carefully balanced atmosphere. The planet breathes heavily in these early days, each exhalation thick with the molecular foundation of future greenhouse warming. Water vapor behaves more mysteriously, its weight shifting with temperature in ways that confound simple atmospheric models. At 18 atomic mass units, H2O molecules should settle below nitrogen, yet their tendency to condense and rise again in convective cycles creates vertical mixing that defies purely gravitational sorting. Steam rises from the molten surface, cools in the thin upper air, then condenses into droplets that fall back toward the heat source in an endless circulation. This early water cycle operates without benefit of oceans or land masses, relying entirely on the temperature gradient between molten rock and the cold vacuum of space above. The atmospheric pressure builds slowly, measured not in familiar units like pounds per square inch, but in the gradual increase of molecular collisions per cubic meter. What began as near-vacuum conditions now supports enough gas density to create visible distortions above volcanic vents, like heat mirages rising from summer pavement. The refractive index of the thickening air begins to bend starlight, creating the first atmospheric scintillation, ancient twinkling that no eyes yet exist to witness. Sulfur compounds add their own peculiar weight to the mixture, with sulfur dioxide molecules carrying 64 atomic mass units each. These heavy gases tend to pool in low-lying areas between volcanic vents, creating localized pockets of dense, reactive atmosphere. The sulfur dioxide slowly oxidizes in the thin air, forming sulfur trioxide that will eventually combine with water vapor to create the first sulfuric acid droplets. These microscopic acid clouds represent chemistry's earliest experiments with atmospheric complexity, molecular interactions that seem almost intentionally designed to test the stability of the growing sky. The planet's rapid rotation, perhaps 6 to 8 hours per day during this Hadean epoch, creates Coriolis effects even in the thin atmosphere. Rising volcanic gases begin to curve slightly as they ascend, following paths that spiral gently eastward or westward depending on their latitude. This atmospheric deflection creates the first hints of large-scale circulation patterns, though the currents remain far too weak and chaotic to establish permanent weather systems. Only took a few 100 million years for the atmosphere to discover the art of circulation, and even then, the patterns shift constantly as volcanic activity waxes and wanes across the planet's surface. Temperature gradients drive much of this early atmospheric sorting. The molten surface radiates heat upward at temperatures exceeding 1200 degrees Celsius, while the upper reaches of the atmosphere approach the near absolute zero of interplanetary space. This extreme temperature differential creates powerful convection currents that mix gases vertically even as gravity tries to sort them by weight. Hot carbon dioxide rises rapidly, cooling and becoming denser as it ascends, then sinking back toward the surface in slow, invisible waterfalls of molecular descent. The atmospheric envelope begins to exhibit its first pressure variations, subtle changes in density that create the earliest version of what meteorologists will eventually call high and low pressure systems. Areas above particularly active volcanic regions develop slightly higher atmospheric pressure as gases accumulate faster than they can disperse. Conversely, regions between major volcanic zones experience lower pressure, creating gentle atmospheric currents that flow from high to low pressure areas at speeds measured in centimeters per hour rather than the kilometers per hour of future wind systems. Scientists studying ancient atmospheric evolution remain puzzled by certain isotopic ratios preserved in rocks from this period. The heavy isotope of sulfur, sulfur-34, appears in concentrations that suggest atmospheric chemistry quite different from modern processes. These isotopic signatures hint at photochemical reactions occurring in the upper atmosphere, driven by solar ultraviolet radiation operating on gas mixtures that no longer exist anywhere in the solar system. The atmospheric laboratory of the Hadean Earth conducted experiments in molecular chemistry that cannot be replicated in modern conditions. Noble gases provide their own mysterious signatures in the geological record. Xenon, with its atomic weight of 131, should have settled quickly toward the surface. Yet isotopic evidence suggests significant amounts escaped to space during this early period. This xenon paradox implies that the early atmosphere was simultaneously thick enough to support complex chemistry, yet thin enough to allow substantial gas loss to the vacuum above. The balance between accumulation and escape created a dynamic equilibrium that shifted constantly as volcanic activity fluctuated. The density stratification creates its own microenvironments at different altitudes. Near the surface, where atmospheric pressure reaches its maximum, molecular collisions occur frequently enough to support complex chemical reactions. Carbon monoxide combines with water vapor to form primitive organic compounds. Hydrogen sulfide reacts with carbon dioxide to create carbon disulfide and other sulfur-bearing molecules. These reactions represent the atmosphere's first experiments with organic chemistry, molecular combinations that will prove essential for life forms still millions of years in the future. Higher in the atmosphere, where gas density decreases towards space, individual molecules travel longer distances between collisions. This rarefied environment favors different types of chemistry, photodissociation reactions driven by solar ultraviolet light, ionization processes that create atmospheric plasma, and the slow escape of light gases to interplanetary space. The upper atmosphere functions as a selective membrane, allowing certain molecules to pass through to space while retaining others for continued circulation within the growing envelope of gases. The weight of this ancient air creates the planet's first barometric pressure. Though the concept of weather forecasting remains inconceivable in a world without seasons, without temperature variation beyond the simple gradient from molten surface to frozen space. Atmospheric pressure varies only with altitude and proximity to major volcanic vents, creating a simple three-dimensional map of gas density that shifts slowly as the planet's geological activity migrates from region to region. This early atmospheric stratification establishes the fundamental architecture that will support all future weather systems. The tendency of gases to sort themselves by weight, modified by temperature gradients and planetary rotation, creates the basic framework upon which complexity will gradually build. Dense gases near the surface will eventually support the flight of insects and birds. Lighter gases in the upper atmosphere will form protective layers that shield the surface from harmful radiation. But for now, the atmosphere remains a simple experiment in molecular sorting, gravity's patient organization of volcanic breath into the layered foundation of future skies. Mountains as sky pillars. The first mountain ranges begin their slow emergence from the molten surface, like geological fingers reaching toward the thin sky. These ancient peaks rise not through the familiar process of tectonic collision. The continents themselves have not yet formed, but through the restless churning of convection cells deep in the planet's mantle. Plumes of superheated rock break through the surface in lines and clusters, cooling into the earliest solid topography that will serve as anchor points for atmospheric circulation. These primordial mountains bear little resemblance to familiar ranges like the Himalayas or the Rockies. They lack the layered sedimentary rocks that speak of ancient seas, the metamorphic cores that record tectonic pressure, or the granite intrusions that mark continental collision zones. Instead, they consist entirely of basaltic rock, dense, dark stone formed from rapidly cooled lava flows. Each peak represents a moment when the planet's interior heat found expression in vertical space, building upward grain by grain as successive eruptions added height to the growing landforms. The atmospheric effects of these early mountains become apparent almost immediately. Rising air masses encounter the solid barriers and are forced upward, creating the first orographic lifting in Earth's history. Warm gases heated by the molten surface flow horizontally until they meet the steep basaltic slopes, then spiral upward along the mountainsides like invisible rivers flowing against gravity. This mechanical lifting creates localized areas of lower atmospheric pressure at the peaks, drawing more air upward in a self-reinforcing cycle that establishes the earliest mountain weather systems. Temperature gradients become more complex as topography interrupts the simple vertical stratification of the early atmosphere. Mountain peaks, extending higher into the thin air, cool more rapidly than the surrounding lowlands. The basaltic rock radiates heat absorbed from the molten surface below, but the decreased atmospheric density at altitude allows this heat to escape more easily to space. Temperature differences of several hundred degrees develop between peak and valley, creating thermal currents that flow both horizontally and vertically through the three-dimensional landscape. Wind patterns begin to emerge as these thermal and topographic effects interact with the planet's rotation. Air heated in the valleys rises and flows toward the cooler mountain peaks, while cooler air from the heights descends to replace the rising warm masses. The Coriolis effect, though still weak in the thin atmosphere, deflects these flows slightly, creating spiral patterns that wrap around the mountain bases like atmospheric whirlpools. These early circulation systems operate at speeds measured in meters per hour rather than the kilometers per hour of modern wind systems, but they represent the first organized movement of air across the planet's surface. The volcanic activity that builds these mountains also modifies local atmospheric chemistry in ways that would not occur over flat terrain. Gases released from mountain vents must travel through more complex pathways, mixing and reacting as they flow around the irregular topography. Carbon dioxide released from a peak vent may flow downhill like an invisible river, pooling in valleys where it reacts with volcanic water vapor to form carbonic acid. Sulfur compounds released at high altitude may travel horizontally for kilometers before descending to lower elevations, creating chemical gradients that vary with both altitude and distance from volcanic sources. The mountains create their own microenvironments for atmospheric chemistry. South-facing slopes, if such directions have meaning on a planet that rotates so rapidly, receive more direct heating from volcanic activity below and solar radiation above. These warmer slopes drive more vigorous convection, creating localized updrafts that carry volcanic gases higher into the atmosphere. North-facing slopes remain cooler, allowing gases to condense and flow downslope in density currents that concentrate heavy molecules like carbon dioxide and sulfur dioxide in the valleys. Scientists studying the geological record from this period find evidence of these early mountain-atmosphere interactions preserved in the chemistry of ancient basalts. Vesicles. Small bubbles frozen in the volcanic rock contain gas samples that reveal the atmospheric composition at different altitudes. Higher elevation basalts show evidence of exposure to more oxidized atmospheric conditions, while valley floor rocks preserve signatures of more reduced chemical environments. These mineral records suggest that atmospheric chemistry varied significantly with topography even in these early times. The erosion of these first mountains begins almost immediately after their formation, but operates through mechanisms unknown in the modern world. Without liquid water to carve valleys or freeze-thaw cycles to crack rock faces, erosion occurs primarily through thermal expansion and contraction. The extreme temperature variations between day and night, perhaps several hundred degrees, as the thin atmosphere provides little thermal buffering, cause the basaltic rock to expand and contract repeatedly. Over thousands of years, this thermal cycling fractures the mountain faces, sending rocky debris cascading down the slopes in slow-motion avalanches that reshape the topography even as new volcanic activity continues to build it upward. The atmospheric effects of this thermal erosion prove surprisingly important for long-term atmospheric evolution. Rock fragments exposed to the thin air present fresh mineral surfaces for chemical weathering reactions. Iron-bearing minerals in the basalt begin to oxidize in the presence of trace amounts of oxygen released by photodissociation of water vapor in the upper atmosphere. This early chemical weathering removes oxygen from the atmosphere faster than volcanic outgassing can replace it, helping to maintain the reducing conditions necessary for certain types of primitive chemistry. Dust and fine particles eroded from the mountain peaks become the atmosphere's first aerosols, microscopic solid particles suspended in the gas mixture. These airborne minerals serve as condensation nuclei for water vapor, creating the earliest clouds around mountain peaks where temperature and humidity conditions favor condensation. The clouds remain thin and ephemeral, more like wisps of steam than the substantial water clouds of later geological periods, but they represent the atmosphere's first experiments with phase changes and precipitation cycles. The spacing between mountain ranges creates natural corridors for atmospheric flow, channels where gases can travel across vast distances without encountering topographic barriers. These early wind corridors establish the foundations for planetary-scale circulation patterns that will persist throughout Earth's history. Air masses heated in one volcanic region can flow through these mountain gaps to reach distant areas, distributing heat and chemical components across continental distances. Only took a few 100 million years to establish the basic geography of atmospheric circulation, and even now, the largest mountain ranges on Earth continue to influence weather patterns in ways that echo these ancient topographic controls. The mountains function as primitive atmospheric mixing devices, creating turbulence that brings gases from different altitudes into contact with each other. Smooth laminar flow over flat terrain allows atmospheric layers to remain separate and unmixed, but the complex airflow around mountain peaks creates eddies and vortices that promote vertical mixing. This turbulent mixing accelerates chemical reactions between atmospheric components and helps to homogenize the composition of the lower atmosphere. The psychological effect of these first mountains on the developing atmospheric system seems almost intentional, as if the planet were experimenting with different ways to organize the interface between solid Earth and gaseous sky. The vertical relief provides structure and complexity to what had been a simple two-dimensional problem of gases overlying molten rock. Now the atmosphere must navigate around obstacles, flow through valleys, and respond to the three-dimensional architecture of an increasingly complex planetary surface. These earliest peaks establish the precedent for all future mountain atmosphere interactions. The orographic lifting, thermal circulation, and chemical weathering processes that begin with these simple basaltic ranges will eventually operate on much larger scales when true mountain building begins with the formation of continental crust. But for now, these modest volcanic mountains serve as the first pillars supporting the growing weight of the atmosphere, providing anchor points for circulation systems that help transform a thin envelope of volcanic gas into the foundational layers of future weather. The ocean's gentle exhale begins as the first stable bodies of liquid water accumulate in the deepest basins between volcanic ranges. These primordial seas form gradually as atmospheric water vapor condenses and flows downhill, gathering in low-lying areas where the molten surface has cooled enough to allow liquid water to persist. The earliest oceans bear little resemblance to modern seas. They remain small, shallow, and extraordinarily hot, with surface temperatures approaching the boiling point of water under the thin atmospheric pressure. Yet even these scalding pools begin the slow process of oceanic breathing that will eventually regulate the planet's entire atmospheric system. Water evaporation from these hot seas creates the first substantial water vapor flux into the atmosphere. Unlike the simple condensation and precipitation of volcanic steam, oceanic evaporation operates as a continuous process driven by the temperature differential between liquid water and the cooler air above. Each square meter of ocean surface releases millions of water molecules per second into the growing atmosphere, creating localized humidity that begins to modify the chemical behavior of other atmospheric gases. The evaporation rate remains enormous by modern standards, perhaps a meter of water depth per day from the hottest pools, yet the small size of these early seas limits their total atmospheric contribution. The chemistry of evaporation proves more complex than simple phase change from liquid to gas. As water molecules escape the ocean surface, they carry with them dissolved salts and volcanic gases that had accumulated in the liquid phase. Sodium chloride crystals form as microscopic aerosols when seawater droplets evaporate completely in the dry air. Dissolved carbon dioxide escapes back to the atmosphere, but at rates controlled by the ocean's surface temperature and the atmospheric CO2 concentration above. This early ocean-atmosphere gas exchange establishes the chemical feedback mechanisms that will eventually stabilize Earth's climate system. Thermal circulation in these primitive oceans drives complex patterns of evaporation that vary across the water surface. Areas where underwater volcanic vents continue to heat the seawater create localized zones of intense evaporation, sending up columns of steam that rise like aquatic geysers into the atmosphere. Cooler regions near the shoreline evaporate more slowly, creating horizontal gradients in atmospheric humidity that begin to influence wind patterns and pressure systems. The ocean's surface becomes a patchwork of different evaporation rates, each contributing its own signature to the atmospheric water budget. The diurnal cycle of heating and cooling creates the planet's first regular pattern of oceanic breathing. During the brief Hadean day, intense solar heating and continued volcanic warming drive vigorous evaporation that loads the atmosphere with water vapor. At night, the rapid cooling of the thin atmosphere causes widespread condensation, sending much of this water vapor back to the ocean's surface as a fine mist of microscopic droplets. This daily breathing cycle moves vast quantities of water between liquid and gas phases, creating the first predictable rhythm in atmospheric water content. Scientists studying the isotopic signatures preserved in ancient minerals find evidence that these early oceans exchanged water with the atmosphere at rates far exceeding anything observed in modern systems. The oxygen isotope ratios in volcanic rocks from this period suggest extremely rapid cycling of water between oceanic and atmospheric reservoirs. This isotopic evidence indicates that the residence time of water molecules in the early atmosphere measured days or weeks rather than the months or years typical of modern atmospheric water vapor. The planet's water cycle operated in fast forward during these early times, perhaps compensating for the much smaller volumes of liquid water available. Ocean surface waves, driven by the earliest wind systems flowing over the water, increase the effective surface area for evaporation by creating countless small droplets and spray. Even the gentle breezes possible in the thin atmosphere generate enough surface roughness to enhance evaporation rates significantly above those of perfectly calm water. The mechanical action of wind-driven waves also helps to mix the ocean's surface layers, bringing warmer water from depth to the surface where it can evaporate more readily. This wave-enhanced evaporation creates a positive feedback loop, where increased atmospheric moisture leads to more complex weather patterns, which in turn drive stronger winds and more vigorous oceanic evaporation. The chemical composition of the early oceans influences their evaporation behavior in ways that seem almost designed to moderate atmospheric conditions. High concentrations of dissolved salts raise the boiling point of seawater, allowing liquid water to persist at higher temperatures than pure water could tolerate. Dissolved volcanic gases like carbon dioxide and hydrogen sulfide lower the pH of the early oceans, affecting the solubility of various compounds and modifying the chemical signature of evaporated water vapor. These chemical effects create subtle differences in evaporation rates that help to regulate the overall water budget of the atmosphere. Oceanic evaporation begins to influence atmospheric pressure patterns through the latent heat effects of phase change. When water evaporates from the ocean surface, it absorbs substantial amounts of thermal energy that are then carried upward with the water vapor. This process cools the ocean surface slightly while adding heat to the atmosphere at higher altitudes, where the water vapor eventually condenses. The vertical redistribution of thermal energy through evaporation and condensation creates the first convective circulation patterns that operate independently of direct surface heating by volcanic activity. The early oceans also begin to absorb atmospheric gases at their surfaces, creating the first substantial reservoirs for chemical species that had previously existed only in gaseous form. Carbon dioxide dissolves readily in the hot seawater, forming dissolved carbonic acid that begins to weather the basaltic rocks of the ocean floor. Atmospheric sulfur dioxide also dissolves efficiently, creating sulfurous acid that contributes to the chemical breakdown of volcanic minerals. This oceanic absorption of atmospheric gases represents the planet's first large-scale atmospheric cleaning mechanism, removing reactive species from the air and sequestering them in liquid reservoirs. Only took several 100 million years for the oceans to discover their role as atmospheric regulators, and even now, the largest bodies of water on Earth continue to breathe with the same fundamental processes that began in these tiny volcanic seas. The evaporation-driven moisture flux from the early oceans creates the first substantial atmospheric humidity, providing the water vapor necessary for more complex weather systems. Dissolved gases escaping from the ocean's surface add their own chemical signatures to the atmospheric mixture, creating feedback loops between oceanic and atmospheric chemistry that will persist throughout Earth's history. The thermal inertia of liquid water begins to moderate the extreme temperature fluctuations that characterize the purely volcanic atmosphere. Ocean surfaces heat more slowly than volcanic rock during the day and cool more slowly at night, creating more stable atmospheric temperatures in coastal regions. This thermal buffering effect extends inland as atmospheric moisture carries oceanic heat away from the shoreline, distributing the moderating influence of liquid water across increasingly large areas of the planet's surface. The earliest tides, driven by lunar gravitational forces acting on these small seas, create additional complexity in oceanic evaporation patterns. The rising and falling water levels expose and submerge different areas of hot volcanic rock, creating periodic changes in the total surface area available for evaporation. Tidal pools that form during low tide concentrate dissolved salts and gases, creating localized zones of enhanced chemical activity that contribute unique signatures to the atmospheric mixture. These primitive oceans establish the foundational relationship between liquid water and atmospheric water vapor that will eventually support all terrestrial life. The oceanic breathing that begins with these hot, salty pools creates the moisture transport mechanisms necessary for weather systems, the chemical buffering required for atmospheric stability, and the thermal regulation essential for maintaining liquid water under a wide range of atmospheric conditions. The ocean's gentle exhale transforms the purely volcanic atmosphere into something more complex and dynamic. breathing life into the space between Earth and sky. Magnetic fields hold the winds in an embrace so gentle that their presence becomes apparent only through absence, the slow hemorrhaging of atmosphere that occurs when planetary magnetism fails. Deep within the molten core of the early Earth, convection currents of liquid iron begin to organize themselves into coherent patterns that generate the planet's first substantial magnetic field. This invisible shield extends thousands of kilometers into space, creating a protective bubble that deflects the charged particles streaming outward from the young sun. Without this magnetic embrace, the solar wind would strip away the carefully accumulated atmosphere faster than volcanic outgassing could replace it. The strength of the early magnetic field fluctuates as the planet's core continues to differentiate, separating heavy iron-nickel alloys from lighter silicate materials. Periods of strong magnetism alternate with intervals of weakened protection, creating episodic variations in atmospheric loss rates that leave subtle signatures in the geological record. During times of strong magnetic shielding, the atmosphere accumulates more rapidly, allowing gas pressures to build and atmospheric chemistry to become more complex. When the magnetic field weakens, increased atmospheric escape to space removes lighter gases preferentially, altering the chemical composition of the remaining air. The solar wind of the young sun carries far more energy than the gentle stellar breeze that bathes the modern solar system. Early stellar evolution produces intense flares and coronal mass ejections that would devastate an unprotected atmosphere. The primitive magnetosphere deflects these charged particle streams around the planet, creating the first auroral displays in the thin upper atmosphere. These ancient auroras differ dramatically from their modern counterparts. They occur at much lower altitudes where the atmosphere barely exists, creating ghostly curtains of ionized gas that flicker and dance above the volcanic landscape. Magnetic field lines threading through the upper atmosphere create pathways for the flow of ionized gases, channeling atmospheric escape along specific routes toward the magnetic poles. This guided atmospheric loss operates more efficiently than simple thermal escape, as charged particles can follow magnetic field lines directly out of the gravitational well rather than requiring enough thermal energy to overcome gravity entirely. The magnetic channeling of atmospheric escape creates preferential loss of certain isotopes and chemical species, gradually altering the composition of the remaining atmosphere in ways that persist throughout Earth's history. The interaction between magnetic fields and atmospheric gases produces the first space weather phenomena in Earth's vicinity. Solar wind particles deflected by the magnetosphere create bow shocks and magnetospheric substorms that inject energy into the upper atmosphere through electromagnetic induction. These energy injections heat the thin air to temperatures of several thousand degrees, creating a hot atmospheric layer that extends the planet's gravitational influence but also enhances thermal escape rates for light gases like hydrogen and helium. Scientists studying paleomagnetism in ancient volcanic rocks find evidence that the early magnetic field underwent frequent reversals, with north and south magnetic poles switching positions on timescales of thousands to millions of years. During these reversal periods, the magnetic field strength drops dramatically, allowing increased atmospheric loss and enhanced bombardment of the surface by cosmic radiation. The geological record suggests that atmospheric composition and pressure varied significantly with these magnetic cycles, creating long-term oscillations in atmospheric conditions that influence the planet's chemical evolution. The magnetic field creates its own three-dimensional architecture in the space surrounding Earth, with field lines that compress on the sunward side and stretch into a long magnetotail on the night side. This asymmetric magnetic geometry influences atmospheric circulation patterns by creating different charged particle environments in different regions around the planet. The compressed day-side magnetosphere allows more solar wind interaction with the upper atmosphere, while the extended night-side tail creates a wake of disturbed magnetic conditions that affects atmospheric escape rates. Charged particles trapped in the early magnetosphere create radiation belts similar to, but much more intense than the modern Van Allen belts. These energetic particle populations interact with atmospheric gases through collision and electromagnetic processes, dissociating molecules and creating ionized layers that affect the propagation of electromagnetic radiation through the atmosphere. The early ionosphere, formed by these radiation belt interactions, creates the first electrically conductive layer in the atmosphere, enabling atmospheric electrical phenomena like primitive lightning discharges. The magnetic protection of the atmosphere operates selectively, preserving some atmospheric components while allowing others to escape preferentially. Light noble gases like helium and neon, which interact weakly with magnetic fields, escape readily regardless of magnetic protection. Heavier gases and those that become ionized in the upper atmosphere experience stronger magnetic protection, leading to atmospheric composition changes that favor the retention of chemically active species over inert ones. This selective retention process helps to concentrate the atmospheric gases most important for subsequent chemical evolution. Only took a few 100 million years for the magnetic field to stabilize into the dipolar structure that still protects Earth's atmosphere today. And even now, variations in magnetic field strength continue to influence atmospheric escape rates and space weather phenomena. The magnetic field's role as atmospheric guardian operates so subtly that its importance becomes clear only when astronomers observe other planets that lack sufficient magnetic protection. Mars, with its weak magnetic field, has lost most of its original atmosphere to space. Venus, despite its strong gravity, suffers atmospheric loss through magnetic field interactions that differ from Earth's protective configuration. The coupling between magnetic fields and atmospheric gases creates feedback mechanisms that help stabilize both systems. Atmospheric gases that become ionized in the upper atmosphere contribute to electrical currents that reinforce the magnetic field structure. Conversely, magnetic field variations influence atmospheric escape rates, which affect the density and composition of the ionosphere, which in turn influences magnetic field generation. This electromagnetic feedback system creates a dynamic equilibrium that helps maintain atmospheric pressure within bounds compatible with liquid water and complex chemistry. Magnetic storms, caused by variations in solar wind intensity interacting with Earth's magnetic field, create temporary disturbances in atmospheric escape rates and upper atmospheric chemistry. During magnetic storms, increased energy input to the upper atmosphere enhances thermal escape rates and creates unusual chemical reaction pathways through enhanced ionization and dissociation processes. These storm-driven atmospheric changes operate on timescales of hours to days, creating short-term variability in atmospheric conditions that adds complexity to the long-term chemical evolution of the air. The magnetic field's influence extends beyond simple atmospheric protection to affect the fundamental physics of gas retention around the planet. Magnetic pressure gradients create forces that can either enhance or oppose gravitational binding of atmospheric gases, depending on the geometry of magnetic field lines and the charge state of atmospheric particles. This magnetic modification of effective gravity creates altitude-dependent variations in atmospheric density that differ from simple hydrostatic equilibrium, adding another layer of complexity to atmospheric structure and circulation patterns. The early magnetosphere also serves as a kind of atmospheric laboratory, creating extreme conditions of temperature, pressure, and electromagnetic field strength that cannot be reproduced anywhere on the planet's surface. Chemical reactions that occur in the magnetosphere contribute unique molecular species to the atmospheric inventory, including exotic ionized compounds and electronically excited states that participate in atmospheric chemistry before relaxing to more stable configurations. These magnetospheric contributions to atmospheric chemistry remain small in absolute terms, but may have played important roles in the synthesis of complex organic molecules. The invisible magnetic embrace that holds Earth's atmosphere creates a protective boundary that defines the edge of the planet's atmospheric influence. Beyond the magnetosphere, space begins in earnest, with particle densities and electromagnetic conditions that bear no resemblance to planetary environments. Within the magnetic boundary, gases can circulate and accumulate, chemistry can operate, and the slow building of atmospheric complexity can proceed. The magnetic field transforms the volume around Earth from empty space into a sheltered environment where atmospheric evolution can unfold over geological timescales, protected from the sterilizing radiation and particle flux of interplanetary space. The first rains remember themselves in the texture of ancient stone, preserving the memory of water's earliest attempts to carve pathways through a landscape that had never known the touch of falling droplets. These initial precipitation events occur sporadically as atmospheric water vapor reaches sufficient concentration to condense around microscopic particles of volcanic dust suspended in the thin air. The raindrops that form remain small and ephemeral, evaporating quickly in the hot, dry atmosphere before reaching the molten surface below. Yet even these brief encounters with gravity begin to establish the vertical pathways that water will follow for billions of years to come. The condensation process operates under conditions so extreme that modern meteorology provides few analogies for understanding early precipitation mechanisms. Atmospheric water vapor concentrations fluctuate wildly as volcanic outgassing pulses and oceanic evaporation rates vary with surface temperature and wind patterns. When humidity levels spike above saturation thresholds, water molecules begin clustering around condensation nuclei, tiny particles of silicate dust, sulfur compounds, and metal oxides ejected from volcanic vents. These primitive cloud condensation nuclei prove far more efficient at triggering precipitation than the organic and salt particles that seed modern raindrops. The chemistry of early rainwater differs dramatically from modern precipitation, carrying dissolved atmospheric gases that create solutions more corrosive than any natural rainwater found today. Carbon dioxide concentrations in the early atmosphere reach levels that produce carbonic acid rain, with pH values approaching those of modern industrial acid precipitation. Sulfur dioxide from volcanic emissions dissolves readily in the water droplets, forming sulfurous acid that attacks exposed rock surfaces with unprecedented chemical aggression. These acidic rains begin the planet's first large-scale chemical weathering processes, dissolving mineral components from volcanic rocks and transporting them as dissolved ions through the earliest hydrological systems. The thermal environment surrounding early precipitation creates unique phase change behaviors that operate unlike any modern weather phenomena. Raindrops forming in the upper atmosphere encounter extreme temperature gradients as they fall through air that cools rapidly with altitude above the scalding surface. Many droplets undergo multiple cycles of freezing and melting during their descent, creating complex internal structures that affect their chemical reactivity and dissolution capacity. Some precipitation reaches the surface as hail-like particles of alternating ice and liquid layers, while other droplets evaporate completely during their fall, leaving behind concentrations of dissolved minerals that seed future precipitation events. The earliest rain patterns establish the fundamental architecture of terrestrial water circulation by creating the first permanent channels for water flow across the planetary surface. Even though individual rain events remain brief and localized, the cumulative effect of thousands of precipitation episodes begins to carve shallow depressions in the cooling volcanic terrain. These proto-valleys follow the steepest gradients available, creating branching networks that converge toward the lowest elevations where the earliest seas accumulate. The erosional patterns carved by primitive rainfall create the topographic framework that will guide water flow throughout Earth's subsequent history. Scientists studying the mineral composition of ancient sedimentary rocks find evidence that early rainwater carried significantly higher concentrations of dissolved metals and rare earth elements than modern precipitation. The extreme chemical reactivity of acidic rainwater interacting with fresh volcanic surfaces creates solutions enriched in iron, magnesium, calcium, and trace elements that will prove essential for future biological processes. These metal-rich solutions accumulate in the earlier sedimentary environments, creating chemical reservoirs that preserve records of atmospheric composition and precipitation chemistry from billions of years ago. The frequency and intensity of early rain events correlate closely with volcanic activity patterns, creating regional variations in precipitation that persist for thousands of years at a time. Areas downwind from major volcanic centers experience more frequent rainfall as water vapor and condensation nuclei concentrations remain consistently elevated. Regions between volcanic zones may experience drought conditions lasting centuries, broken only by occasional precipitation events triggered by atmospheric circulation patterns that transport moisture from distant sources. These long-term precipitation cycles create diverse chemical weathering environments that contribute to the heterogeneous composition of early sedimentary deposits. Evaporation of rainwater from hot surfaces creates localized humidity patterns that influence subsequent precipitation events through positive feedback mechanisms. Areas that receive rainfall become temporarily more likely to experience additional precipitation as the evaporating water increases local atmospheric moisture content. This precipitation-evaporation feedback creates clustering of rain events that helps to concentrate erosional processes in specific geographic regions while leaving other areas relatively unaffected by chemical weathering. The clustering effect amplifies the landscape-shaping power of early precipitation beyond what would be expected from random rainfall distribution. The isotopic composition of water in early precipitation provides clues about the sources and cycling pathways of atmospheric moisture during this period. Oxygen isotope ratios in precipitated water reveal the relative contributions of oceanic evaporation versus direct volcanic water vapor to atmospheric humidity. Hydrogen isotope signatures indicate the degree of isotopic fractionation occurring during multiple evaporation and condensation cycles, suggesting that early atmospheric water underwent more complex cycling patterns than simple evaporation and precipitation. These isotopic records preserved in ancient minerals provide the only direct evidence for precipitation chemistry and atmospheric water cycling during Earth's earliest history. Only took several 100 million years for rainfall to establish the basic patterns of terrestrial water circulation that continue to operate today. And even now, modern precipitation follows many of the same topographic pathways first carved by these ancient acidic rains. The erosional channels created by early precipitation events guide the flow of modern rivers and streams, creating a direct physical connection between contemporary landscapes and the chemical weathering processes that began in the Hadean atmosphere. The memory of first rains persists in the geometry of modern watersheds and the mineral composition of sedimentary rocks derived from early weathering processes. The interaction between rainfall and volcanic landscapes creates the planet's first large-scale geochemical cycles, moving chemical elements between atmospheric, surface, and subsurface reservoirs through dissolution, transport, and precipitation processes. Elements dissolved from volcanic rocks by acidic rainwater travel through surface drainage systems to accumulate in sedimentary basins where they participate in new mineral formation processes. This early geochemical cycling establishes the precedent for the complex biogeochemical cycles that will eventually support terrestrial life, creating pathways for essential elements to move between different environmental compartments. Lightning, associated with early precipitation events, adds another dimension to atmospheric chemistry by creating high-energy environments where unusual chemical reactions can occur. Electrical discharges in the moisture-laden atmosphere above volcanic regions generate nitric oxide through nitrogen fixation processes, creating nitrate compounds that dissolve in rainwater to form nitric acid. These lightning-generated nitrogen compounds represent the atmosphere's first experiments with nitrogen chemistry beyond simple volcanic outgassing, creating chemical pathways that will become essential for biological nitrogen cycling in later geological periods. The cumulative effect of countless early precipitation events gradually transforms the planetary surface from a uniform molten environment to a landscape of increasing topographic and chemical complexity. Rain-carved valleys create sheltered environments where different chemical conditions can develop, leading to spatial variations in mineral formation and weathering processes. The erosional and depositional processes driven by early precipitation create the first substantial topographic relief beyond simple volcanic construction, establishing the foundation for more complex landscape evolution and the eventual development of diverse terrestrial habitats. The memory embedded in stone speaks of water's patient persistence in transforming planetary surfaces through the simple but inexorable process of falling from sky to earth. Each raindrop carries within its molecular structure the chemical signature of atmospheric composition, volcanic activity, and surface temperature conditions that existed at the moment of its formation. These chemical memories accumulate in sedimentary deposits that preserve detailed records of early atmospheric evolution and climate change, creating an archive of planetary history written in the language of dissolved minerals and isotopic ratios. Stromatolites whisper oxygen into the ancient seas through the quiet revolution of cyanobacteria. Those microscopic pioneers that discover the art of capturing sunlight and exhaling the gas that will eventually transform Earth's entire atmospheric chemistry. These layered mounds of microbial mats grow slowly in the shallow margins of early oceans, where volcanic heat and solar radiation create conditions suitable for the planet's first experiments with photosynthesis. Each stromatolite represents millions of generations of bacterial cells living, dying, and calcifying in thin layers that accumulate like geological whispers, building structures that rise centimeter by centimeter above the seafloor. The cyanobacteria, responsible for these early stromatolites, operate photosynthetic machinery of startling sophistication, splitting water molecules to harvest electrons while releasing oxygen as a metabolic waste product. This process requires the coordination of hundreds of protein complexes and cofactors working in precise synchronization to capture photons, separate charges, and drive the chemical reactions that convert carbon dioxide and water into organic compounds. The biochemical complexity involved in oxygenic photosynthesis suggests that these organisms represent the culmination of extensive evolutionary experimentation rather than life's first tentative steps toward harnessing solar energy. The oxygen production rates of early stromatolite communities remain modest by modern standards, perhaps equivalent to the photosynthetic output of a small pond covered with algae. Yet, in the context of an atmosphere that had never before encountered significant oxygen concentrations, even these small biological emissions begin to create profound chemical changes in the surrounding environment. Dissolved iron in the early oceans reacts immediately with the newly produced oxygen. Forming iron oxide precipitates that settle to the seafloor in thin layers that will eventually become banded iron formations, some of the most distinctive geological signatures of early atmospheric evolution. The spatial distribution of stromatolite growth creates the first biogeographic patterns in Earth's history, with different microbial communities establishing themselves in environments that suit their particular metabolic requirements. Shallow, well-lit areas near volcanic vents support the most vigorous stromatolite growth, where warm temperatures and abundant carbon dioxide create optimal conditions for photosynthesis. Deeper or more shadowed regions develop different microbial assemblages that rely on chemosynthesis or fermentation rather than photosynthesis, creating a mosaic of metabolic strategies across the early seafloor. The daily rhythm of photosynthesis in stromatolite communities creates the first predictable biological cycling of atmospheric gases, with oxygen production peaking during daylight hours and ceasing completely at night. This diurnal variation in biological gas exchange adds a new temporal dimension to atmospheric chemistry, creating short-term fluctuations in oxygen concentration that interact with longer-term geological processes. The day-night cycling of biological oxygen production establishes metabolic rhythms that will eventually synchronize with planetary rotation cycles and influence the evolution of circadian timing mechanisms in all subsequent life forms. Scientists studying the microscopic structure of ancient stromatolites find evidence for remarkably sophisticated microbial communities that included multiple species working in metabolic cooperation. Photosynthetic cyanobacteria in the upper layers of stromatolite mats produce oxygen and organic compounds that support heterotrophic bacteria in the lower layers, while anaerobic bacteria at the base of the mats recycle nutrients and maintain chemical conditions suitable for continued growth. This early example of ecological partnership demonstrates that complex community interactions evolved very early in life's history, well before the appearance of multicellular organisms. The chemical microenvironments within stromatolite mats create gradients of oxygen concentration, pH, and nutrient availability that span ranges equivalent to major global environmental changes compressed into vertical distances of just a few millimeters. The uppermost layers of the mats experience oxygen concentrations that may approach modern atmospheric levels during peak photosynthesis, while deeper layers remain completely anoxic and chemically reducing. These steep chemical gradients within individual stromatolites provide diverse ecological niches that support the evolution of metabolic diversity in early microbial communities. The process of stromatolite formation involves complex interactions between biological processes and inorganic mineral precipitation that create feedback loops between life and geology. Photosynthetic bacteria alter the local chemistry of seawater by removing carbon dioxide and producing oxygen, changing the saturation levels of various minerals and promoting the precipitation of calcium carbonate and other compounds. These mineral precipitates become incorporated into the stromatolite structure, creating a permanent geological record of biological activity while also modifying the physical environment in ways that influence subsequent microbial growth patterns. Only took about 2 billion years for stromatolite communities to produce enough oxygen to fundamentally alter Earth's atmospheric chemistry. And, even now, modern stromatolites in places like Shark Bay, Australia, continue to operate through the same basic photosynthetic processes that began in these ancient microbial mats. The oxygen-producing machinery developed by early cyanobacteria remains essentially unchanged in modern photosynthetic organisms, from marine phytoplankton to terrestrial forests, creating a direct biochemical connection between contemporary oxygen production and these ancient stromatolite communities. The isotopic signatures preserved in stromatolite minerals provide evidence for the earliest biological fractionation of carbon isotopes, with organic matter showing preferential incorporation of the lighter carbon, 12 isotope compared to inorganic carbonate minerals. This biological isotope fractionation creates distinctive chemical signatures that allow geochemists to identify biological activity in rocks billions of years old, even when direct fossil evidence has been obliterated by subsequent geological processes. The carbon isotope records from stromatolites provide some of the earliest unambiguous evidence for life on Earth. The growth patterns of stromatolite laminations reflect seasonal and longer-term environmental cycles, creating chronological records that preserve information about early climate patterns and ocean chemistry changes. Thicker laminations correspond to periods of rapid growth during favorable conditions, while thinner layers record times of environmental stress or reduced photosynthetic activity. These growth records enable scientists to reconstruct environmental conditions in early oceans with remarkable temporal resolution, revealing cycles of productivity that correlate with orbital variations and volcanic activity patterns. The ecological impact of early stromatolite communities extends far beyond their direct oxygen production to include the creation of the first substantial organic carbon reservoirs in Earth's surface environment. Dead microbial biomass accumulating around stromatolite structures creates organic-rich sedimentary layers that remove carbon dioxide from the atmosphere while providing energy sources for heterotrophic organisms. This early biological carbon sequestration helps to moderate atmospheric carbon dioxide concentrations and establishes the foundation for the complex carbon cycling that will eventually regulate Earth's climate system. The chemical warfare that develops within stromatolite communities creates the first evolutionary pressure for the development of antioxidant systems and oxygen tolerance mechanisms in living organisms. The oxygen produced by photosynthetic bacteria proves toxic to many anaerobic organisms that had evolved in the oxygen-free environment of early Earth, forcing rapid evolution of protective mechanisms or extinction. This oxygen crisis represents one of the first major evolutionary bottlenecks in Earth's history, fundamentally reshaping the composition of microbial communities and driving the evolution of aerobic metabolism. The physical structure of stromatolites creates the first substantial modification of seafloor topography by biological processes. Building reef-like structures that alter local water circulation patterns and create sheltered environments for other organisms. The irregular surfaces of stromatolite mounds trap sediment particles and create microenvironments with different light levels, current speeds, and chemical conditions. These biologically constructed habitats provide the template for the much more complex reef ecosystems that will eventually develop when multicellular organisms evolve the ability to build large-scale biological structures. The whispered conversations between stromatolite bacteria occur through chemical signaling mechanisms that coordinate community behavior across spatial scales ranging from micrometers to meters. Quorum sensing systems allow bacterial cells to monitor population density and coordinate activities like biofilm formation and metabolic switching in response to environmental conditions. These early examples of microbial communication establish the precedent for the complex chemical signaling networks that will eventually evolve in multicellular organisms and ecological communities. The legacy of stromatolite oxygen production persists in the fundamental chemistry of Earth's atmosphere and oceans, with every breath of modern air containing oxygen molecules that trace their ancestry back to these ancient microbial communities. The photosynthetic machinery that enabled stromatolite bacteria to split water and release oxygen represents one of the most important biochemical innovations in Earth's history, creating the oxidizing atmospheric conditions that would eventually support complex multicellular life and the diverse ecosystems of the modern world. Iron rusts the world red as oxygen molecules released by stromatolite communities encounter the vast reservoirs of dissolved iron that fill the early oceans like liquid metal, waiting for its first breath of oxidation. The iron exists primarily as ferrous iron Fe2+, a reduced form that dissolves readily in the oxygen-free seawater of the Archean oceans. When the first traces of biological oxygen diffuse into these iron-rich waters, chemical reactions begin that will paint the seafloor in bands of red and black, creating some of the most distinctive geological formations in Earth's rock record, while simultaneously cleansing the atmosphere of its early oxygen burden. The oxidation of dissolved iron proceeds through a cascade of chemical reactions that transform soluble ferrous iron into insoluble ferric iron oxides. As oxygen concentrations rise locally around stromatolite communities, Fe2+ ions encounter dissolved oxygen molecules and undergo rapid oxidation to Fe3+, which immediately precipitates as iron hydroxide minerals that settle toward the seafloor like rusty snow. This chemical precipitation removes both iron and oxygen from the seawater, creating a self-regulating system that prevents oxygen concentrations from rising too rapidly in the early oceans, while gradually concentrating iron oxides in sedimentary layers. The banded iron formations that result from this process create alternating layers of iron-rich and iron-poor sediments that record fluctuations in ocean chemistry with remarkable precision. Dark bands rich in magnetite and hematite alternate with lighter bands composed primarily of chert and other silicate minerals, creating striped patterns that reflect seasonal or longer-term cycles in biological oxygen production and iron availability. Each band represents thousands of years of gradual accumulation, building sedimentary sequences hundreds of meters thick that preserve detailed records of early atmospheric evolution. The chemistry of iron oxidation creates complex feedback loops between biological oxygen production and atmospheric oxygen concentrations that help to buffer the planet's early atmospheric evolution. As stromatolite communities produce more oxygen, increased iron oxidation removes this oxygen from the environment before it can accumulate to levels that might prove toxic to the oxygen-sensitive organisms that dominated early ecosystems. This iron buffering system allows gradual adaptation to increasing oxygen levels while preventing catastrophic oxidation events that could sterilize early microbial communities. The spatial patterns of iron oxide precipitation create the first large-scale redox boundaries in Earth's oceans, with oxic zones around stromatolite communities grading into anoxic regions where dissolved iron persists in its reduced form. These redox boundaries migrate seasonally and annually as biological oxygen production varies with environmental conditions, creating dynamic chemical fronts that concentrate various trace elements and create diverse microenvironments for early life. The redox gradients associated with iron oxidation provide energy sources for chemosynthetic bacteria and create ecological niches that support increased microbial diversity. Scientists studying the mineral composition of banded iron formations find evidence for surprisingly complex iron oxide mineralogy that reflects varying oxygen concentrations and chemical conditions during precipitation. Different iron oxide minerals, magnetite, hematite, goethite, and others form under specific combinations of oxygen concentration, pH, and temperature, creating mineralogical records that preserve detailed information about early ocean chemistry. The preservation of these mineral assemblages through billions of years of geological time provides direct evidence for the chemical conditions that existed during Earth's transition from an anoxic to an oxic world. The global distribution of banded iron formations reveals that iron oxidation occurred simultaneously across multiple ocean basins, suggesting that biological oxygen production reached planetary scales during the Great Oxidation Event. Iron formations of similar age and composition appear on every continent, indicating that the chemical processes driving iron oxidation operated as part of a global ocean system rather than as isolated local phenomena. This worldwide synchronicity demonstrates the planetary scope of early biological influences on atmospheric and ocean chemistry. The isotopic composition of iron in banded iron formations provides evidence for the biological origin of the oxygen responsible for iron oxidation, with sulfur isotope signatures that differ markedly from those produced by purely chemical processes. Mass-independent sulfur isotope fractionation preserved in iron formations older than 2.4 billion years indicates atmospheric chemistry dominated by photochemical reactions in an oxygen-free environment. The disappearance of these signatures in younger ion formations marks the transition to an oxygen-rich atmosphere where biological processes dominate sulfur cycling. Only took about 300 million years for iron oxidation to remove most of the dissolved iron from Earth's oceans, effectively ending the major phase of banded iron formation while allowing atmospheric oxygen concentrations to begin their rise toward modern levels. This iron removal process represents one of the largest geochemical transformations in Earth's history, transferring billions of tons of iron from dissolved oceanic reservoirs to solid sedimentary deposits while fundamentally altering the chemical environment available for early life. The depletion of dissolved iron from the oceans creates new challenges and opportunities for early life forms, forcing the evolution of more efficient iron acquisition mechanisms while opening ecological niches for organisms adapted to oxic environments. Iron-limited conditions in post-banded iron formation oceans drive the evolution of sophisticated iron transport and storage systems in marine microorganisms, creating biochemical innovations that persist in modern life forms. The transition from iron-rich to iron-limited oceans represents a fundamental ecological transition that influences marine productivity and community structure throughout subsequent Earth history. The formation of iron oxide minerals creates the first substantial repositories for trace elements that will prove essential for later biological evolution, with banded iron formations serving as geological reservoirs for elements like nickel, cobalt, and molybdenum. These trace metals become incorporated into iron oxide crystal structures during precipitation, creating concentrated deposits that will eventually be weathered and recycled through surface environments where they can support biological processes. The trace element chemistry of banded iron formations influences the availability of micronutrients in surface environments for billions of years following their formation. The physical properties of iron oxide minerals affect the mechanical behavior of early sedimentary rocks, creating some of the most durable and chemically resistant formations in the geological record. The high density and chemical stability of iron oxides help preserve banded iron formations through billions of years of tectonic activity and metamorphism, maintaining detailed records of early atmospheric evolution even as surrounding rocks undergo extensive alteration. These preservation properties make banded iron formations some of the most important sources of information about Earth's early environmental history. The economic importance of banded iron formations extends far beyond their scientific value to include some of the world's largest iron ore deposits, providing the raw materials for modern steel production and industrial civilization. The iron concentrated by early biological processes continues to support human technology billions of years after its initial precipitation, creating a direct material connection between early life processes and contemporary society. The rust that paints ancient rocks red provides the iron that builds modern skyscrapers and infrastructure. The aesthetic impact of banded iron formations creates some of the most visually striking geological exposures on Earth, with alternating red and black bands that create natural artwork on scales ranging from hand specimens to cliff faces hundreds of meters high. The rhythmic banding patterns reflect the temporal cycles that governed early ocean chemistry, creating visual representations of time that allow observers to see the rhythm of ancient environmental change preserved in stone. These geological formations provide tangible connections to Earth's early history that communicate the drama of atmospheric evolution through pattern and color. The end of major banded iron formation deposition marks a critical transition in Earth's environmental history, representing the moment when biological oxygen production finally overwhelmed the planet's capacity to consume oxygen through iron oxidation and other chemical processes. This transition sets the stage for the accumulation of free oxygen in the atmosphere and oceans, creating the oxidizing conditions that will eventually support complex multicellular life while driving the extinction of many anaerobic organisms adapted to the reducing conditions of early Earth. The red bands of oxidized iron that stripe ancient rock faces serve as monuments to the first great atmospheric crisis in Earth's history, preserving evidence of the chemical revolution that transformed a reducing planet into an oxidizing world. Each layer of rusty sediment records the patient work of early life forms, gradually changing the fundamental chemistry of Earth's surface environment, creating the foundation for all subsequent atmospheric and biological evolution through the simple but profound process of learning to breathe. Continental shelves catch clouds like geological nets stretched beneath the atmospheric ocean, providing the first stable platforms where air masses can rest, cool, and release their accumulated moisture in patterns that begin to resemble recognizable weather systems. These broad, shallow underwater terraces form as the earliest continental crust achieves sufficient buoyancy to rise above the surrounding oceanic basalt, creating extensive areas of relatively shallow water that extend hundreds of kilometers from the emerging shorelines. The thermal and topographic effects of these submerged continental margins begin to influence atmospheric circulation in ways that fundamentally alter precipitation patterns and moisture distribution across the planet's surface. The shallow water over continental shelves heats more rapidly during the day than the deeper oceanic basins, creating temperature contrasts that drive convective circulation between continental and oceanic air masses. Warm air rising from sun-heated shelf waters draws in cooler air from above the deeper oceans, establishing the first primitive sea breeze circulation systems. These thermal circulation patterns operate on daily cycles that follow the rhythm of solar heating, creating predictable wind patterns that transport moisture from oceanic evaporation sources toward the continental margins where it can precipitate and contribute to terrestrial freshwater systems. The extensive area of continental shelves creates vastly expanded surface zones for ocean-atmosphere heat exchange, amplifying the thermal effects that drive atmospheric circulation. Unlike the deep ocean basins where thermal energy disperses through large volumes of water, the shallow shelf environments concentrate solar heating in thin water layers that respond rapidly to changes in solar radiation. This enhanced thermal responsiveness makes continental shelf regions into atmospheric heat engines that generate more vigorous convection and stronger circulation patterns than purely oceanic environments. The irregular topography of emerging continental crust creates complex patterns of shallow and deep water across the shelf regions, with submerged hills and valleys that modify local circulation patterns in increasingly sophisticated ways. Shallow areas over submerged ridges heat more intensely and drive stronger updrafts, while deeper channels between these features channel airflow and create localized wind patterns. This three-dimensional complexity in shelf topography begins to create the kind of mesoscale circulation features that characterize modern coastal weather systems. The chemical composition of continental crust influences the weathering reactions that occur as atmospheric moisture interacts with exposed and near-surface rocks on the continental shelves. Granitic and other felsic rock types that compose much of the early continental crust weather differently than the basaltic rocks that dominate oceanic regions, releasing different suites of dissolved ions into the shallow shelf waters. These chemical differences between continental and oceanic weathering products begin to create distinct chemical signatures in atmospheric moisture that originates from different geographic regions. Scientists studying the sedimentary record from ancient continental shelf environments find evidence for remarkably complex circulation patterns that transported sediments across vast distances during the early stages of continental emergence. Cross-bedded sandstones and other current-generated sedimentary structures indicate persistent wind-driven circulation that operated consistently enough to create large-scale sediment transport systems. The orientation and scale of these sedimentary features suggest atmospheric circulation patterns that operated on continental scales, driven by the thermal contrasts between shelf and deep ocean environments. The seasonal cycle of solar heating creates annual patterns of enhanced and reduced circulation intensity over continental shelves, with stronger thermal contrasts during summer months driving more vigorous atmospheric circulation. Winter conditions with reduced solar heating allow the shelf waters to cool toward the temperature of surrounding deep ocean water, reducing thermal contrasts and weakening the circulation systems. These seasonal variations in circulation intensity create annual cycles of precipitation and wind patterns that begin to establish the temporal framework for continental climate systems. The extensive continental shelves provide platforms for the development of tide pool ecosystems and intertidal environments that create additional complexity in local atmospheric moisture patterns. Tidal cycles expose and submerge large areas of shelf surface, creating periodic changes in the total surface area available for evaporation and heat exchange. The alternating exposure and submersion of tidal zones creates diurnal cycles of moisture release that add temporal complexity to the already spatially complex circulation patterns generated by shelf topography. Only took a few 100 million years for continental shelves to establish their role as fundamental controls on atmospheric circulation patterns, and even now, the world's major continental shelves continue to generate the coastal circulation systems that dominate weather patterns for billions of people living near sea level. The thermal contrasts between land and sea that drive modern monsoon systems and coastal weather patterns operate through the same basic mechanisms that began with the emergence of the first continental shelves from the Archean oceans. The biological productivity that develops over continental shelves creates additional feedbacks with atmospheric circulation through the release of biological gases and aerosols that modify cloud formation and precipitation processes. Early marine ecosystems concentrated in the nutrient-rich shallow waters over continental shelves begin producing dimethyl sulfide and other organic compounds that serve as cloud condensation nuclei, enhancing precipitation efficiency and creating positive feedback loops between biological productivity and atmospheric moisture cycling. The sediment plumes generated by rivers flowing across continental shelves create atmospheric effects through the release of fine particles that serve as additional condensation nuclei for cloud formation. The suspended sediment loads carried by early rivers create turbid water conditions over large areas of continental shelves, affecting the optical properties of the water surface and modifying heat absorption patterns. These sediment-driven changes in surface properties create additional complexity in the thermal circulation patterns that govern shelf-atmosphere interactions. The development of coral reefs and other biological structures in shallow shelf environments begins to modify wave patterns and water circulation in ways that affect local atmospheric conditions. Biological reef construction creates barriers to water flow that modify the temperature and salinity patterns of shelf waters, which in turn influences evaporation rates and the moisture content of air masses forming over these regions. The three-dimensional structure created by early reef ecosystems adds biological complexity to the physical and chemical processes that control atmospheric circulation. The acoustic properties of continental shelf environments create the first substantial underwater sound channels that affect marine ecosystems and potentially influence atmospheric conditions through their effects on marine biological behavior. Sound waves traveling through shallow shelf waters encounter different reflection and refraction patterns than those in deep ocean environments, creating acoustic landscapes that influence the behavior of marine organisms and their metabolic activities. Changes in marine biological activity can affect the release of biological gases that influence atmospheric chemistry and circulation patterns. The vulnerability of continental shelf environments to atmospheric circulation patterns creates feedback loops where weather systems modify the very shelf environments that generate them, establishing dynamic relationships between atmospheric and marine conditions that operate on multiple timescales. Storm systems generated by shelf circulation can modify seafloor sediment patterns and biological communities, which in turn alter the physical and biological properties that drive subsequent circulation patterns. These feedback loops create complex, non-linear relationships between atmospheric and marine systems that resist simple prediction or analysis. The role of continental shelves as atmospheric moisture collectors becomes increasingly important as global climate patterns develop and continental configurations evolve through plate tectonic processes. Different arrangements of continental shelves relative to ocean basins and atmospheric circulation patterns create different global precipitation patterns and climate zones. The positions and orientations of major continental shelf systems influence the transport of moisture between oceanic and continental environments, affecting the development of terrestrial ecosystems and the evolution of continental climate patterns. The memory of ancient continental shelves persists in modern seafloor topography and sedimentary geology, with relict shelf features that continue to influence contemporary atmospheric and oceanic circulation patterns. Ancient shelf edges and sedimentary deposits create underwater topographic features that affect modern ocean currents and water mass properties, which in turn influence contemporary climate patterns and weather systems. The geological inheritance of early continental shelf development continues to shape atmospheric circulation patterns billions of years after the original shelf formation processes. The snowball Earth sleeps beneath a crystalline dome of ice that stretches from pole to pole, transforming the planet into a gleaming sphere that reflects sunlight back to space with such efficiency that the atmosphere grows thin and quiet above the frozen surface. This global glaciation begins gradually as atmospheric carbon dioxide concentrations decline through enhanced weathering and biological processes, reducing the greenhouse warming that had maintained liquid oceans for billions of years. Ice sheets advance from the polar regions toward the equator, their white surfaces creating an albedo feedback that accelerates cooling by reflecting ever more solar radiation away from the planet's surface. The ice that encases the planet reaches thicknesses of several kilometers in some regions, creating a frozen landscape unlike anything in Earth's subsequent history. The weight of accumulated ice depresses the underlying continental crust, while the removal of water from the oceans lowers global sea level by more than 100 meters. Volcanic islands and continental margins that had been submerged beneath warm seas now stand exposed as isolated peaks and ridges protruding through the ice sheet, creating a stark topography of white ice interrupted by dark volcanic rock. The atmosphere above this frozen world becomes remarkably stable and stratified, with virtually no water vapor to drive convective circulation or weather systems. Atmospheric pressure drops significantly as water vapor, normally a major component of atmospheric mass, becomes locked in the ice sheets below. The thin, dry air circulates sluggishly around the planet in simple patterns driven primarily by solar heating differences between the sunlit and dark hemispheres. Wind speeds remain low throughout most of the atmosphere, creating an almost motionless envelope of gases above the silent ice. Temperature gradients between the equatorial and polar regions nearly disappear as ice coverage approaches global extent, eliminating the thermal contrasts that normally drive large-scale atmospheric circulation. The equatorial ice receives more direct solar radiation than polar ice, but the high reflectivity of snow and ice surfaces prevents significant warming even at the planet's midsection. Surface temperatures remain well below freezing across all latitudes, creating a world where atmospheric circulation operates under conditions that have no modern analog. The chemical composition of the atmosphere shifts dramatically during the snowball glaciation as various gas cycling processes slow or cease entirely. Biological processes that normally release and consume atmospheric gases become severely limited by the extreme cold and lack of liquid water. Volcanic outgassing continues to add carbon dioxide and other gases to the atmosphere, but weathering reactions that normally consume these gases operate much more slowly on frozen surfaces. This imbalance between gas sources and sinks creates a gradual accumulation of volcanic gases in the atmosphere despite the overall atmospheric thinning. Scientists studying the geological record from snowball Earth periods find evidence for remarkably pure ice compositions that suggest very limited atmospheric dust and aerosol concentrations during global glaciation. Ice core samples from these ancient glacial periods, preserved in rare locations where the ice has not been subsequently melted or metamorphosed, show chemical compositions that indicate extremely clean atmospheric conditions with minimal volcanic ash or biological particles. The clarity and chemical purity of snowball Earth ice reflects atmospheric conditions dominated by simple gas circulation without the complex aerosol chemistry of ice-free periods. The isolation of liquid water reservoirs beneath the ice creates unique environments where atmospheric gas exchange becomes severely limited, allowing the evolution of unusual chemical conditions in both the isolated water bodies and the overlying atmosphere. Small pockets of liquid water may persist in geothermally heated areas beneath the ice, creating isolated ecosystems that operate independently of atmospheric gas exchange. These refugia develop their own chemical signatures that differ markedly from both the overlying atmosphere and the normal ocean chemistry of ice-free periods. The duration of snowball Earth episodes, lasting perhaps millions to tens of millions of years, allows atmospheric composition to drift towards states that differ significantly from normal interglacial conditions. The slow accumulation of volcanic carbon dioxide and other gases during the long glacial periods creates atmospheric compositions that have no equivalent in Earth's ice-free history. Trace gases that normally cycle rapidly through biological and weathering processes accumulate to unusual concentrations, creating atmospheric chemistry that approaches equilibrium with volcanic outgassing alone. Only took several million years for each snowball Earth episode to transform completely the chemical and physical state of the atmosphere. And even now, computer models struggle to reproduce the extreme atmospheric conditions that must have existed during global glaciation. The combination of high albedo, thin atmosphere, and disrupted gas cycling creates a climate state so different from modern conditions that understanding snowball Earth atmospheres requires assumptions about atmospheric physics and chemistry that cannot be tested against contemporary observations. The escape of atmospheric gases to space accelerates during snowball Earth conditions as the reduced atmospheric pressure and altered circulation patterns modify the planet's ability to retain its gaseous envelope. Light gases like hydrogen and helium escape more readily from the thin atmosphere, while the reduced water vapor content eliminates much of the atmospheric mass that normally helps retain other gases through gravitational effects. This enhanced atmospheric escape creates long-term changes in atmospheric composition that persist even after the ice sheets eventually melt. The optical properties of the snowball Earth atmosphere create unique radiative conditions where solar radiation penetrates easily through the thin, clear air, but reflects efficiently from the white surface below. The lack of clouds and water vapor eliminates most atmospheric absorption of solar radiation, creating an atmosphere that functions more like a transparent window than the complex radiative environment of ice-free periods. These clear sky conditions allow maximum solar heating of any exposed dark surfaces, creating intense thermal contrasts between ice-covered and ice-free areas. The magnetic field interactions with the thin snowball Earth atmosphere create enhanced atmospheric escape processes that modify atmospheric composition through preferential loss of certain gas species. The reduced atmospheric density allows solar wind particles to penetrate deeper into the atmosphere, creating ionization and heating effects that enhance thermal escape rates. Charged particles in the thin atmosphere follow magnetic field lines more efficiently than in denser atmospheric conditions, creating enhanced polar escape processes that preferentially remove light gases and ions. The volcanic activity that continues throughout Snowball Earth episodes creates localized atmospheric effects that differ dramatically from the global background conditions, with volcanic gas plumes rising through the thin atmosphere to create temporary local weather systems. The reduced atmospheric density allows volcanic gases to reach higher altitudes than normal, creating stratospheric effects that can influence atmospheric circulation on continental scales. These volcanic perturbations to the otherwise stable snowball atmosphere create episodic circulation patterns that redistribute gases and heat around the planet, the gradual warming that eventually ends. Snowball Earth episodes begins with the accumulation of volcanic carbon dioxide to concentrations that finally overcome the albedo feedback of global ice coverage, creating rapid atmospheric and climate changes that transform the planet from icehouse to greenhouse conditions within geologically brief periods. The transition from snowball to normal climate states involves dramatic changes in atmospheric pressure, composition, and circulation that operate much faster than the gradual cooling that initiates glaciation. The memory of snowball Earth conditions persists in the atmospheric system through isotopic signatures and chemical reservoirs that preserve evidence of the extreme atmospheric states that existed during global glaciation. Rare gases trapped in Ice Age minerals retain the isotopic compositions of snowball Earth atmospheres, providing direct evidence for atmospheric conditions that differ markedly from all subsequent atmospheric states. These chemical memories create long-term influences on atmospheric evolution that extend far beyond the duration of individual glacial episodes. The silence that characterizes snowball Earth atmospheres the absence of wind. Weather and atmospheric turbulence creates acoustic conditions unlike any other period in Earth's history, with sound transmission through the thin, stable air following patterns that have no modern equivalent. The frozen landscape eliminates most sources of atmospheric sound generation, creating a world where acoustic communication over long distances becomes possible through the still air. This acoustic transparency may have influenced the evolution of early life forms that survived the glaciation in isolated refugia. Volcanic warmth returns to the frozen world through the patient persistence of geological processes that operate independently of surface temperature, slowly building concentrations of greenhouse gases in the thin atmosphere until the ice sheets begin their inevitable retreat toward the poles. Deep within the Earth's mantle, convection currents continue their ancient circulation patterns, carrying heat from the planet's radioactive core toward the surface in plumes of molten rock that eventually find expression through volcanic eruptions. These eruptions puncture the ice sheets at scattered locations around the globe, creating dark patches of exposed rock and volcanic ash that begin to absorb solar radiation more efficiently than the surrounding white ice. The carbon dioxide released by volcanic activity accumulates gradually in the snowball Earth atmosphere, building concentrations that may reach levels hundreds of times greater than modern atmospheric CO2 content. Without active weathering processes to consume this volcanic carbon dioxide, and with biological processes severely limited by the extreme cold, the greenhouse gas concentrations climb steadily over millions of years. The volcanic CO2 creates an increasingly effective thermal blanket that begins to trap solar radiation reflected from the ice surface, slowly raising atmospheric temperatures despite the high albedo of the frozen landscape. The first signs of warming appear around volcanic vents and geothermal areas where ice begins to thin and develop dark patches that absorb more solar radiation than pure white snow. These initial melt zones create positive feedback loops where reduced ice cover leads to increased solar absorption, which accelerates melting and creates larger areas of dark surface. The expanding melt zones eventually connect to form networks of ice-free areas that spread outward from volcanic centers like slowly growing patches of open water in a frozen sea. The liberation of liquid water from melting ice creates the first substantial water vapor additions to the snowball Earth atmosphere in millions of years, adding another powerful greenhouse gas to the warming atmosphere. Water vapor concentrations remain low initially due to the cold atmospheric temperatures, but even small amounts of atmospheric moisture create significant additional greenhouse warming that accelerates the melting process. The return of water vapor to the atmosphere also restores the possibility of weather systems and precipitation cycles that had been absent during the peak glacial conditions. The chemical composition of meltwater from ancient ice sheets differs dramatically from modern natural waters, carrying dissolved atmospheric gases that had accumulated during the long glacial period. The melting ice releases not only liquid water, but also concentrated solutions of carbon dioxide, sulfur compounds, and other volcanic gases that had been trapped in the ice for millions of years. These chemical releases create temporary atmospheric perturbations and contribute unusual dissolved components to the newly forming rivers and lakes. Scientists studying the geological transitions that mark the end of snowball Earth episodes find evidence for remarkably rapid climate changes that transform global conditions within thousands rather than millions of years. Sedimentary sequences show abrupt transitions from glacial deposits to carbonate rocks typical of warm, tropical seas, indicating that the warming process accelerates dramatically once critical thresholds are crossed. These rapid climate transitions suggest that the snowball Earth climate system operates near tipping points where small changes in forcing can trigger large changes in atmospheric and surface conditions. The atmospheric pressure begins to increase as water vapor returns to the air and volcanic outgassing continues without the consumption by weathering reactions that had been suppressed during peak glacial conditions. The thickening atmosphere creates more effective greenhouse warming and begins to support more vigorous circulation patterns as temperature gradients develop between ice-covered and ice-free regions. The restoration of atmospheric density also reduces the escape of gases to space, helping to retain the volcanic emissions that drive continued warming. The returning atmospheric moisture enables the formation of clouds for the first time in millions of years, creating complex radiative effects that both enhance and moderate the warming process. Clouds reflect solar radiation back to space, creating a cooling effect that partially counteracts greenhouse warming, but they also trap long-wave radiation emitted by the surface, contributing additional greenhouse warming. The net effect of returning cloud cover depends on cloud altitude, thickness, and composition in ways that create complex feedbacks between atmospheric moisture and climate warming. Only took a few thousand years for volcanic greenhouse warming to trigger the irreversible collapse of global ice coverage. And even now, the geological record preserves evidence of these dramatic climate transitions in rock sequences that show rapid changes from glacial to tropical conditions. The speed of snowball Earth termination demonstrates the potential for rapid climate change when atmospheric greenhouse gas concentrations exceed critical thresholds, providing analogs for understanding potential rapid climate changes in other planetary atmospheres. The enhanced volcanic activity that occurs during ice sheet melting creates additional atmospheric effects through the release of ash and aerosols that temporarily modify atmospheric radiative properties. Volcanic eruptions through melting ice sheets create explosive interactions between hot magma and cold ice that generate large quantities of volcanic ash and gas. These volcanic emissions create temporary cooling effects through atmospheric shading while simultaneously contributing greenhouse gases that promote long-term warming. The restoration of liquid oceans begins at low latitudes where solar heating remains most intense despite global ice coverage, creating the first substantial evaporation sources for atmospheric water vapor in millions of years. The newly formed tropical oceans warm rapidly under the enhanced greenhouse conditions, reaching temperatures that may exceed those of modern tropical seas. These hot oceans drive vigorous evaporation that further increases atmospheric water vapor concentrations and accelerates global warming through enhanced greenhouse effects. The chemical weathering of freshly exposed rock surfaces begins almost immediately as liquid water returns to the landscape, creating new pathways for atmospheric carbon dioxide consumption that will eventually help moderate the extreme greenhouse conditions. The enhanced weathering operates on rock surfaces that had been protected from chemical attack during the long glacial period, creating fresh mineral surfaces that react rapidly with carbonic acid formed from atmospheric CO2 and water. This renewed weathering begins the long process of removing excess atmospheric carbon dioxide and returning climate conditions toward more moderate states. The biological recovery that follows snowball Earth termination begins with the rapid expansion of organisms that had survived in isolated refugia during the glacial period, creating sudden increases in biological productivity that affect atmospheric composition through enhanced oxygen production and carbon dioxide consumption. Early post-glacial ecosystems operate under atmospheric conditions quite different from those that existed before glaciation, requiring rapid adaptation to higher CO2 concentrations and altered ocean chemistry. The isotopic signatures preserved in rocks that formed during snowball Earth termination provide evidence for dramatic changes in atmospheric and ocean chemistry that accompanied the transition from icehouse to greenhouse conditions. Carbon isotope ratios in post-glacial carbonate rocks show distinctive patterns that reflect the unusual atmospheric chemistry of the warming period, with isotopic compositions that differ markedly from both glacial and normal interglacial conditions. These isotopic records provide direct evidence for the extreme atmospheric states that existed during the transition periods. The global nature of snowball Earth termination creates synchronous warming effects that appear simultaneously in geological records from all continents, demonstrating that atmospheric greenhouse warming operates as a global phenomenon that affects planetary climate as an integrated system. The rapid warming process overwhelms regional climate variations and creates globally uniform warming trends that persist until new equilibrium conditions develop between atmospheric greenhouse gases and surface temperature conditions. The memory of volcanic rescue from global glaciation persists in the geological record as distinctive rock sequences that preserve evidence of the extreme climate transitions that ended snowball Earth episodes, creating geological markers that allow scientists to identify and study these dramatic climate events billions of years after they occurred. The rock record of snowball Earth termination provides some of the most direct evidence available for understanding how atmospheric greenhouse effects can drive rapid global climate change under extreme conditions. Ozone forms its shield in the highest reaches of the atmosphere, where ultraviolet radiation from the sun encounters oxygen molecules and splits them into reactive fragments that recombine in ways that create Earth's first protective chemical barrier against the sterilizing radiation of space. This process begins slowly as atmospheric oxygen concentrations rise above the threshold necessary to support ozone formation, perhaps 2% of modern atmospheric oxygen levels. Individual oxygen molecules. O2 absorb high-energy ultraviolet photons and dissociate into single oxygen atoms that quickly bond with other oxygen molecules to form ozone O3 in reactions that occur primarily between 20 and 50 kilometers above the surface. The chemistry of ozone formation requires a delicate balance of atmospheric conditions that took hundreds of millions of years to achieve, involving not only sufficient oxygen concentrations, but also the right atmospheric pressure and temperature profiles to maintain stable ozone layers. Too little oxygen provides insufficient raw material for ozone production, while atmospheric conditions that are too dense or too thin prevent the photochemical reactions from proceeding efficiently. The early atmosphere gradually develops the precise combination of oxygen abundance, pressure gradients, and solar radiation intensity necessary to sustain significant ozone production. The vertical distribution of ozone concentration creates the first chemically distinct atmospheric layer, with peak ozone densities occurring at altitudes where the balance between ozone production and destruction reaches optimal conditions. Below about 15 kilometers altitude, atmospheric density remains too high for efficient ozone formation, while above 60 kilometers, insufficient oxygen concentrations limit ozone production despite optimal photochemical conditions. This vertical concentration gradient creates a distinct stratospheric ozone layer that fundamentally alters the atmospheric radiation environment and establishes new patterns of atmospheric heating and circulation. The formation of the ozone layer creates profound changes in atmospheric temperature structure by absorbing ultraviolet radiation that had previously penetrated to the surface and converting this radiant energy into atmospheric heat. The absorption of UV radiation by ozone creates a temperature inversion in the stratosphere, with temperatures increasing rather than decreasing with altitude, as occurs in the lower atmosphere. This temperature inversion establishes the thermal structure that defines the stratosphere as a distinct atmospheric layer and creates circulation patterns that differ markedly from tropospheric weather systems. The protective effect of ozone against biological damage becomes apparent as ultraviolet radiation flux at the surface drops to levels that allow photosynthetic organisms to venture into previously uninhabitable shallow water environments. Before ozone formation, UV radiation penetrated several meters into oceanic water, creating sterile zones where photosynthetic bacteria could not survive despite adequate light for photosynthesis. The ozone shield reduces surface UV intensity sufficiently to allow photosynthetic organisms to colonize the upper few meters of oceanic water, dramatically expanding the volume of biologically productive ocean environment. Scientists studying the atmospheric photochemistry of ozone formation find that the process involves complex catalytic cycles where trace atmospheric components can dramatically enhance or inhibit ozone production and destruction rates. Nitrogen oxides, produced by lightning and volcanic activity, serve as catalysts that can either promote ozone formation or accelerate ozone destruction depending on their concentrations and altitude distributions. These catalytic effects mean that ozone layer stability depends not only on oxygen concentrations, but also on the atmospheric abundance of numerous trace gases that participate in stratospheric photochemistry. The seasonal variations in solar radiation intensity create annual cycles of ozone production that establish the first regular atmospheric chemical rhythms operating on yearly timescales. During summer months, increased UV radiation drives enhanced ozone production, while winter conditions with reduced solar intensity allow ozone concentrations to decline through destruction reactions that continue in the absence of photochemical production. These seasonal ozone cycles create corresponding variations in atmospheric heating patterns and stratospheric circulation that begin to influence surface weather systems through stratosphere-troposphere coupling mechanisms. The global circulation patterns in the stratosphere distribute ozone from its primary production regions at low latitudes toward the polar regions through large-scale atmospheric motions that operate much more slowly than tropospheric weather systems. This meridional ozone transport creates latitudinal gradients in ozone concentration that result in geographic variations in UV protection, with higher ozone concentrations at high latitudes providing enhanced protection during polar summer when solar radiation remains intense for extended periods. The transport of ozone by stratospheric circulation establishes global patterns of UV protection that influence the geographic distribution of early photosynthetic ecosystems. Only took about 400 million years for atmospheric oxygen concentrations to reach levels sufficient to maintain a stable ozone layer. And even now, the photochemical processes that create and destroy stratospheric ozone operate through the same basic mechanisms that first formed Earth's protective radiation shield. The contemporary ozone layer continues to shield the surface from harmful UV radiation while participating in complex atmospheric chemistry that influences climate and weather patterns through radiative and dynamical coupling between the stratosphere and troposphere. The formation of the ozone layer enables the first substantial expansion of life into terrestrial environments by reducing UV radiation to levels compatible with biological processes operating in the absence of water's protective absorption. Photosynthetic organisms that had been confined to aquatic environments where water provided UV protection can begin to colonize land surfaces and shallow water environments where direct solar radiation had previously created lethal conditions. This expansion of habitable environments represents one of the most important consequences of ozone layer formation for biological evolution. The chemical destruction of ozone occurs through reactions with atmospheric trace gases that can catalytically remove ozone molecules much faster than natural production processes can replace them, creating atmospheric chemistry feedback loops that can destabilize the ozone layer under certain conditions. Volcanic emissions containing chlorine and bromine compounds can trigger ozone destruction cycles that temporarily reduce stratospheric ozone concentrations and increase surface UV radiation. These natural ozone depletion events provide analogs for understanding how human activities might affect stratospheric ozone chemistry. The interaction between ozone and other atmospheric gases creates complex photochemical smog reactions that produce additional trace compounds in the stratosphere, establishing the first substantial atmospheric organic chemistry that operates independently of biological processes. Photochemical reactions involving ozone, hydrocarbons, and nitrogen oxides create a variety of organic compounds that participate in additional atmospheric chemistry and contribute to the growing complexity of atmospheric composition. These photochemical processes establish the foundation for the complex atmospheric chemistry that characterizes modern planetary atmospheres. The radiative effects of ozone extend beyond UV absorption to include interactions with long-wave radiation that contribute to atmospheric greenhouse warming, making ozone both a UV shield and a greenhouse gas that influences surface temperatures. The dual radiative role of ozone creates complex climate feedbacks where changes in ozone concentrations affect both UV radiation flux and thermal radiation balance, influencing surface temperature and atmospheric circulation patterns. These multiple radiative effects make ozone layer changes important drivers of climate variation on timescales ranging from seasonal to geological. The stability of the ozone layer depends on maintaining atmospheric conditions that favor ozone production over ozone destruction, requiring continued volcanic and biological sources of atmospheric oxygen, as well as limited concentrations of ozone-destroying catalysts. Changes in volcanic activity, biological productivity, or atmospheric circulation patterns can shift the balance between ozone production and destruction, creating long-term variations in ozone layer thickness and UV protection. The geological record preserves evidence for past variations in ozone layer stability that correlate with major changes in atmospheric composition and biological evolution. The formation of Earth's ozone shield represents one of the most important atmospheric developments in planetary history, creating the radiation protection necessary for complex life to eventually colonize terrestrial environments while establishing stratospheric chemistry and circulation patterns that continue to influence global climate and weather systems. The invisible dome of ozone molecules that forms high above the surface creates a protective barrier that enables the expansion of life beyond aquatic environments while adding new complexity to atmospheric structure and composition that persists throughout subsequent atmospheric evolution. Trade winds find their paths across the vast oceanic expanses as the planet's rotation and thermal gradients combine with stabilizing continental configurations to create the first persistent, large-scale circulation patterns that will transport heat, moisture, and chemical components around the globe for billions of years. These great rivers of moving air establish themselves gradually as the continents achieve sizes and positions that create substantial thermal contrasts with the surrounding oceans, while the planet's rotation rate stabilizes sufficiently to generate consistent Coriolis effects that deflect moving air masses into predictable curved trajectories. The thermal engine that drives these nascent trade wind systems operates through temperature differences between sun-heated continental masses and the more thermally stable oceanic regions, creating pressure gradients that draw air from high-pressure zones over cooler surfaces toward low-pressure areas above warmer regions. During daylight hours, continental surfaces heat more rapidly than adjacent ocean waters, creating rising air masses over land that draw in marine air from offshore. At night, the continents cool more quickly than the oceans, reversing the pressure gradients and creating offshore airflow that carries continental air masses toward the sea. The Coriolis effect, generated by the planet's rotation, deflects these thermal circulation patterns into the curved trajectories that define trade wind behavior, with air masses flowing from subtropical high-pressure zones toward equatorial low-pressure regions while curving westward due to rotational effects. In the northern hemisphere, this deflection creates northeasterly trade winds, while southern hemisphere air masses curve to create southeasterly trades. These deflected airflows establish the first persistent wind belts that encircle the planet, creating atmospheric circulation patterns that operate independently of local thermal variations. The oceanic surfaces over which these early trade winds flow provide vast reservoirs of thermal inertia that help stabilize atmospheric circulation patterns by moderating temperature extremes and maintaining consistent evaporation sources for atmospheric moisture. The trade winds passing over warm ocean surfaces pick up water vapor through evaporation, creating moisture-laden air masses that transport oceanic heat and humidity toward continental regions. This oceanic moisture transport begins the process of atmospheric heat redistribution that will eventually moderate global climate patterns and support terrestrial precipitation systems. The convergence of trade wind systems from northern and southern hemispheres creates the first intertropical convergence zone, a belt of atmospheric instability and enhanced precipitation that migrates seasonally with changes in solar heating patterns. The meeting of northeasterly and southeasterly trade winds creates atmospheric lifting that promotes cloud formation and precipitation, establishing a zone of enhanced weather activity that follows the seasonal migration of maximum solar heating. This convergence zone becomes a persistent feature of global atmospheric circulation that influences precipitation patterns across tropical regions. Scientists studying the sedimentary record from early trade wind periods find evidence for remarkably consistent atmospheric circulation patterns that transported dust and other aerosols across oceanic distances with sufficient regularity to create distinctive geological deposits. Wind-blown sediments preserved in marine cores show grain-size distributions and mineral compositions that indicate persistent atmospheric transport from specific continental source regions to distant oceanic deposition sites. These aeolian deposits provide direct evidence for trade wind circulation patterns that operated with surprising consistency over millions of years. The establishment of persistent trade wind patterns creates the first reliable atmospheric transport mechanisms for biological dispersal, allowing marine organisms to spread across oceanic distances through wind-driven transport of spores, seeds, and other propagules. Early marine ecosystems begin to show biogeographic patterns that reflect atmospheric circulation influences, with species distributions that correlate with prevailing wind directions and seasonal circulation changes. The trade winds become highways for biological exchange that help establish the global connectivity of early marine ecosystems. The seasonal migration of trade wind belts follows the annual cycle of solar heating, creating predictable patterns of wet and dry seasons that establish the first regular climate rhythms in continental regions. During summer months, enhanced solar heating shifts atmospheric circulation patterns poleward, bringing tropical moisture to higher latitudes, while winter cooling moves the circulation belts toward the equator, creating drier conditions in subtropical regions. These seasonal circulation changes create annual precipitation cycles that begin to influence continental weathering patterns and biological productivity. Only took several 100 million years for trade wind circulation to establish the basic pattern of atmospheric heat and moisture transport that continues to dominate global weather systems today. And even now, the northeast and southeast trade winds follow the same fundamental circulation patterns that first developed when continental configurations achieved sufficient size and stability to drive persistent thermal circulation. Modern satellite observations of trade wind patterns reveal circulation structures that echo the ancient atmospheric dynamics established during Earth's early continental evolution. The chemical transport accomplished by trade wind circulation begins to homogenize atmospheric composition on global scales by mixing air masses from different continental and oceanic source regions, reducing regional variations in atmospheric chemistry that had characterized earlier periods when circulation patterns remained localized and variable. The persistent mixing of atmospheric gases by trade wind circulation helps establish more uniform global atmospheric composition while facilitating the transport of volcanic gases and biological emissions across continental distances. The interaction between trade winds and oceanic surface currents creates coupled atmosphere-ocean circulation systems that enhance the efficiency of global heat transport beyond what either atmospheric or oceanic circulation could accomplish independently. Trade winds driving oceanic surface currents help establish persistent ocean circulation patterns that transport warm water poleward and cold water equatorward, while oceanic heat transport moderates atmospheric temperature gradients and stabilizes trade wind circulation patterns. These coupled circulation systems create positive feedback loops that reinforce persistent atmospheric and oceanic circulation. The vertical structure of trade wind circulation creates distinct atmospheric layers with different circulation characteristics, establishing the first clear separation between surface wind systems and upper-level atmospheric circulation patterns. Trade winds operate primarily within the lower few kilometers of the atmosphere, while upper-level return circulation transports air masses in the opposite direction at higher altitudes. This vertical circulation structure creates atmospheric overturning cells that efficiently transport heat and moisture between different latitudinal zones. The persistence of trade wind patterns creates the first atmospheric circulation features that operate as stable climate system components rather than transient weather phenomena, establishing circulation patterns that influence global climate on timescales ranging from seasonal to geological. Unlike the chaotic circulation patterns that characterize local weather systems, trade wind belts maintain their basic structure and position through decades and centuries of environmental variation. This atmospheric stability provides a foundation for more complex climate system development. The geographic extent of trade wind circulation encompasses most of the global ocean surface between about 30 degrees north and south latitude, creating the first truly planetary-scale atmospheric circulation system that influences environmental conditions across multiple continents and ocean basins. The trade wind belts establish atmospheric circulation patterns that affect weather and climate across vast areas of the planet's surface, creating the first evidence for atmospheric circulation as a global rather than regional phenomenon. The influence of trade wind circulation on continental climate patterns begins to create predictable geographic zones of enhanced and reduced precipitation that will eventually support the development of distinct terrestrial biomes and ecosystems. Regions that receive consistent moisture transport from oceanic trade, wind circulation, develop different vegetation patterns and weathering regimes than areas that remain in atmospheric rain shadows or experience primarily continental air masses. These circulation-driven climate patterns establish the geographic framework for terrestrial ecosystem development. The acoustic properties of persistent trade wind circulation create the first substantial atmospheric soundscapes that operate on planetary scales, with wind-generated sounds that can propagate across oceanic distances through atmospheric and oceanic sound channels. The consistent flow of trade wind circulation generates atmospheric turbulence and surface wave patterns that create characteristic sound signatures that differ from the acoustic environments generated by more variable local circulation patterns. These planetary-scale acoustic environments may influence the evolution of biological communication systems in marine organisms. The sky learns to hold weather in layered chambers of air that stratify according to temperature, pressure, and chemical composition, creating the familiar atmospheric architecture of troposphere, stratosphere, and higher layers that will cradle all future meteorological phenomena within their distinct thermal and chemical environments. This atmospheric stratification emerges gradually as solar heating, surface cooling, and chemical processes establish temperature profiles that create stable layers where air masses of different densities remain separated by invisible boundaries that persist for thousands of years. The troposphere forms as the lowest atmospheric layer where weather systems can develop and persist, extending from the surface to altitudes where temperature stops decreasing with height and begins to increase due to ozone absorption of solar radiation. Within this turbulent lower layer, convective circulation driven by surface heating creates vertical mixing that homogenizes atmospheric composition while generating the temperature and pressure variations that drive wind systems, storm formation, and precipitation cycles. The troposphere becomes Earth's weather laboratory, where atmospheric moisture, thermal energy, and chemical components interact to create the complex meteorological phenomena that will eventually support terrestrial ecosystems. The tropopause establishes itself as a stable thermal boundary that separates the turbulent troposphere from the calmer stratosphere above, creating an atmospheric ceiling that contains most weather activity within the lower atmospheric layer. This temperature inversion boundary acts as a lid that prevents most convective circulation from extending into the stratosphere, concentrating weather phenomena within the tropospheric volume where surface heating can drive atmospheric instability. The tropopause height varies with latitude and season, creating a flexible but persistent barrier that shapes the vertical development of atmospheric circulation systems. The stratosphere develops its characteristic temperature structure through ozone absorption of ultraviolet radiation, creating a warm layer above the troposphere where atmospheric circulation operates through different mechanisms than surface-driven convection. Stratospheric circulation patterns move much more slowly than tropospheric weather systems, creating a stable atmospheric environment where trace gases can persist for months or years rather than the days or weeks typical of tropospheric residence times. This slow circulation allows stratospheric chemistry to operate on longer time scales and creates atmospheric reservoirs for chemical species that influence tropospheric composition. The mesosphere and thermosphere extend the atmospheric layering to progressively higher altitudes where decreasing density and increasing solar radiation create extreme temperature and chemical conditions that bear little resemblance to surface atmospheric environments. These upper atmospheric layers serve as transition zones between the dense lower atmosphere and the near vacuum conditions of space, creating environments where atmospheric gases can escape to space while cosmic radiation begins to influence atmospheric chemistry through ionization and dissociation processes. Scientists studying the development of atmospheric layering find evidence that the thermal structure of the atmosphere has remained remarkably stable once ozone concentrations reached sufficient levels to drive stratospheric heating, suggesting that atmospheric stratification represents a fundamental organizing principle for planetary atmospheres. Temperature profiles measured in ancient ice cores and preserved in mineral compositions show atmospheric thermal structures that closely resemble modern atmospheric layering, indicating that the basic architecture of atmospheric layers has persisted for hundreds of millions of years. The chemical separation between atmospheric layers creates distinct environments for different types of atmospheric chemistry, with tropospheric reactions dominated by surface emissions and biological processes, while stratospheric chemistry operates primarily through photochemical reactions driven by solar ultraviolet radiation. Each atmospheric layer develops its own characteristic chemical composition and reaction pathways, creating a vertically stratified atmospheric chemistry system where different molecular processes dominate at different altitudes. This chemical layering adds complexity to atmospheric composition and creates multiple pathways for atmospheric chemical evolution. The circulation patterns within each atmospheric layer operate according to different physical principles, with tropospheric circulation driven primarily by surface heating and rotation effects, while stratospheric circulation responds more to solar heating and planetary wave propagation. The different circulation characteristics of each layer create complex interactions between atmospheric levels, with disturbances in one layer influencing circulation patterns in adjacent layers through mechanical and radiative coupling mechanisms. These interlayer interactions create three-dimensional atmospheric circulation systems that operate as integrated planetary scale phenomena. only took a few 100 million years for atmospheric layering to establish the thermal and chemical structure that continues to organize atmospheric processes today. And, even now, the basic pattern of tropospheric weather beneath stratospheric ozone heating provides the framework for all meteorological phenomena and atmospheric chemistry. Modern atmospheric science recognizes the same fundamental layer structure that first developed when atmospheric composition and solar radiation reached the conditions necessary to support stable thermal stratification. The development of persistent atmospheric layers creates the first stable platforms for the evolution of altitude-specific atmospheric phenomena, with different types of clouds, precipitation, and chemical reactions becoming characteristic of specific atmospheric levels. High-altitude cirrus clouds form in the upper troposphere where temperatures remain consistently below freezing, while low-altitude cumulus clouds develop in the warm, moist air near the surface. This altitude-specific cloud formation creates predictable patterns of atmospheric optical properties and precipitation characteristics. The pressure gradients that develop between atmospheric layers create vertical atmospheric circulation systems that transport gases, heat, and moisture between different altitude levels, establishing the three-dimensional atmospheric circulation that enables complex weather system development. Rising air masses in the troposphere carry surface heat and moisture to higher altitudes, where cooling and condensation release latent heat that drives continued vertical circulation. These vertical circulation systems create the atmospheric convection that powers thunderstorms, hurricanes, and other dramatic weather phenomena. The residence times of atmospheric gases vary dramatically between different atmospheric layers, with tropospheric gases cycling rapidly through surface exchange processes, while stratospheric gases may persist for years before returning to lower atmospheric levels. This difference in residence times creates atmospheric reservoirs with different chemical compositions and response times to environmental changes. Gases released at the surface mix rapidly through the troposphere, but require months or years to reach stratospheric altitudes where they may undergo different chemical transformations. The radiative properties of each atmospheric layer contribute differently to planetary energy balance, with tropospheric water vapor and clouds dominating greenhouse warming, while stratospheric ozone provides both greenhouse warming and ultraviolet protection. The layered structure of atmospheric radiative effects creates complex climate feedback systems where changes in one atmospheric layer can influence radiative balance and climate conditions through multiple pathways. These radiative interactions between atmospheric layers help stabilize global climate while creating sensitivity to atmospheric composition changes. The acoustic properties of atmospheric layering create altitude-dependent sound propagation characteristics that influence atmospheric acoustic phenomena and biological communication systems that rely on atmospheric sound transmission. Sound waves propagating through different atmospheric layers encounter varying density, temperature, and composition conditions that affect acoustic transmission efficiency and frequency characteristics. These altitude-dependent acoustic environments create diverse soundscapes that may influence the evolution of biological acoustic communication. The evolutionary pressure created by atmospheric layering influences the development of organisms adapted to different atmospheric environments, with surface-dwelling organisms experiencing different atmospheric chemical and physical conditions than those adapted to high-altitude environments. The variation in atmospheric pressure, oxygen concentration, and ultraviolet radiation exposure between different altitudes creates diverse ecological niches that drive biological adaptation and speciation. These altitude-dependent environmental gradients become important factors in biological evolution and ecosystem development. The stability of atmospheric layering provides a foundation for the development of predictable weather patterns and seasonal climate cycles that enable biological adaptation to atmospheric environmental variation, creating the atmospheric predictability necessary for complex ecosystem development. The consistent thermal and chemical structure of atmospheric layers allows biological organisms to adapt to predictable atmospheric conditions while providing the atmospheric circulation necessary for global heat and moisture transport that moderates climate extremes. The memory of atmospheric layer formation persists in the geological record through mineral compositions and isotopic signatures that preserve evidence of atmospheric thermal structure and chemical composition during different periods of atmospheric evolution, providing direct evidence for the long-term stability of atmospheric layering as a fundamental organizing principle for planetary atmospheres. These geological records demonstrate that atmospheric stratification represents one of the most persistent and important characteristics of Earth's atmospheric system. Giants rest in stone and air as the geological forces that built Earth's atmosphere settle into slow, eternal rhythms that will persist for billions of years, with tectonic plates breathing through thermal expansion and contraction, while magnetic fields pulse with the planet's core circulation and atmospheric layers respond to solar heating with the patient regularity of celestial clockwork. These planetary giants, the mountain ranges that anchor atmospheric circulation, the ocean basins that regulate moisture transport, the magnetic field that shields atmospheric gases from solar wind erosion, and the stratified atmospheric layers that organize weather systems continue their ancient work with a consistency that creates the stable foundation for all subsequent atmospheric and biological evolution. The mountains breathe with thermal rhythms that operate on timescales ranging from daily heating cycles to the million-year periods of tectonic uplift and erosion, creating atmospheric circulation patterns that persist through vast spans of geological time. Each mountain range establishes orographic circulation systems that funnel atmospheric moisture, create precipitation patterns, and modify wind flow in ways that influence regional climate for tens of millions of years. The Himalayas affect Asian monsoon patterns. The Andes control South American precipitation gradients, and the Rockies channel North American storm systems through atmospheric circulation mechanisms that echo the earliest mountain-atmosphere interactions of the Archean era. The ocean basins serve as vast atmospheric regulators, moderating temperature extremes through their enormous thermal inertia while providing moisture sources that maintain atmospheric humidity and drive global precipitation cycles. The Pacific Ocean alone contains enough thermal energy to power atmospheric circulation for centuries without additional solar heating, while the Atlantic Ocean's meridional circulation transports tropical heat to polar regions through atmospheric and oceanic coupling mechanisms that operate continuously regardless of seasonal or annual climate variations. These oceanic giants maintain atmospheric stability through their sheer mass and thermal persistence. The magnetic field generators deep within Earth's core continue their convective circulation patterns that create the protective magnetosphere, deflecting solar wind particles and cosmic radiation that would otherwise strip away atmospheric gases and sterilize the surface. The magnetic field strength varies on timescales ranging from years to millions of years, but maintains sufficient intensity to preserve Earth's atmospheric envelope against the erosive effects of solar activity. This invisible giant operates through electromagnetic forces that extend thousands of kilometers into space while being generated by convection currents in molten iron that circulate at depths of thousands of kilometers below the surface. The atmospheric layers maintain their thermal stratification through radiative heating and cooling processes that operate with remarkable consistency despite variations in solar output, volcanic activity, and biological productivity. The troposphere continues to host weather systems within its convective circulation patterns, while the stratosphere maintains its temperature inversion through ozone heating, and higher atmospheric layers respond to solar radiation according to physical principles that have remained constant throughout Earth's atmospheric evolution. These atmospheric giants organize meteorological phenomena within stable vertical structures that persist through major climate changes. Scientists studying the long-term stability of these atmospheric and geological giants find evidence for feedback mechanisms that help maintain planetary environmental conditions within ranges compatible with liquid water and complex chemistry despite major external perturbations. Ice ages, volcanic catastrophes, asteroid impacts, and other dramatic environmental changes create temporary disruptions in atmospheric and geological systems. But the fundamental organizing principles that govern mountain building, ocean circulation, magnetic field generation, and atmospheric stratification reassert themselves and restore stable environmental conditions within geologically brief recovery periods. The coupling between these different planetary giants creates synergistic effects that enhance environmental stability beyond what any individual system could achieve in isolation, with tectonic activity driving volcanic outgassing that maintains atmospheric composition while mountain building creates circulation patterns that distribute heat and moisture globally. Ocean circulation transports heat between latitudes while providing moisture for atmospheric circulation, and magnetic field protection preserves atmospheric gases that might otherwise escape to space. These interconnected systems create planetary-scale environmental regulation that operates through multiple overlapping mechanisms. The rhythms established by these geological and atmospheric giants create the temporal framework for all biological evolution, with tectonic cycles providing long-term environmental variation that drives evolutionary adaptation, while atmospheric circulation creates seasonal and annual cycles that enable biological timing mechanisms. The magnetic field reversal cycle creates periodic increases in cosmic radiation that may influence mutation rates and evolutionary change, while ocean circulation variations create climate cycles that affect global biological productivity and species distributions. Only took about 4 billion years for these planetary giants to establish the stable environmental conditions that support complex life. And even now, their continued operation maintains the atmospheric and geological conditions necessary for technological civilization and global ecosystems. The mountains, oceans, magnetic fields, and atmospheric layers that support contemporary environmental conditions operate through the same fundamental processes that began when Earth first developed substantial atmospheric mass and geological complexity. The predictability of these large-scale environmental systems enables long-term climate forecasting and environmental planning that would be impossible if atmospheric and geological processes operated chaotically rather than according to consistent physical principles. Weather prediction relies on understanding atmospheric circulation patterns established by mountain ranges and ocean temperature gradients, while climate models depend on representing the thermal and chemical processes that govern atmospheric layer behavior and oceanic heat transport. The resilience of these planetary giants to external perturbations provides confidence that Earth's environmental systems can withstand substantial disruption while maintaining the basic atmospheric and geological functions necessary for continued habitability. Past episodes of environmental crisis, from snowball Earth glaciations to mass extinction events, demonstrate that Earth's atmospheric and geological systems possess self-regulating mechanisms that restore environmental stability even after major disruptions to normal planetary operations. The aesthetic appreciation of these planetary giants extends beyond their scientific importance to encompass their role in creating the landscapes, seascapes, and atmospheric phenomena that define human experience of the natural world. Mountain ranges create the scenic vistas that inspire artistic expression. Ocean systems generate the weather patterns that create diverse regional climates, and atmospheric layers produce the optical phenomena that create sunsets, rainbows, and aurora displays that connect contemporary observers with the same atmospheric processes that have operated throughout Earth's history. The philosophical implications of understanding these planetary giants include recognition that human civilization exists within environmental systems that operate on spatial and temporal scales, that dwarf human experience while maintaining the stable conditions necessary for biological and technological development. The mountains that anchor atmospheric circulation, the oceans that regulate global climate, the magnetic fields that protect atmospheric integrity, and the atmospheric layers that organize weather systems represent planetary-scale phenomena that create the environmental foundation for all terrestrial life. The responsibility that comes with understanding these planetary systems includes recognition that human activities can influence atmospheric and geological processes that have operated consistently for billions of years, potentially disrupting environmental stability mechanisms that have supported life throughout Earth's history. Changes in atmospheric composition, ocean chemistry, and surface temperature patterns can affect the operation of planetary giants that maintain environmental conditions within ranges compatible with complex ecosystems and technological civilization. The continuity between ancient and modern atmospheric processes creates direct connections between contemporary environmental conditions and the geological and atmospheric evolution that began when Earth first developed substantial atmospheric mass and surface complexity. The air we breathe, the weather systems that provide precipitation, and the magnetic field that protects us from cosmic radiation operate through mechanisms that connect us directly with the planetary giants that have maintained Earth's habitability throughout its history. The eternal rhythms of stone and air continue their patient work, maintaining the atmospheric and geological conditions that support life through processes that operate with consistency that spans geological time while responding flexibly to environmental changes that require adaptive responses to maintain planetary habitability. The ancient dance continues in whispers now, as the great atmospheric engines that once roared with volcanic fury settle into the quiet rhythms that will sustain all future life. The sky that was once held up by geological giants now holds itself through the patient circulation of air masses that have learned to flow around mountain ranges, across ocean basins, and through the layered chambers of atmosphere with the consistency of planetary breathing. Each molecule of oxygen carries the memory of stromatolite communities that first discovered the art of splitting water and exhaling gas into ancient seas. Each droplet of rain remembers the pathways carved by acidic precipitation that fell when the world was young and volcanic. The mountains continue their thermal breathing, expanding with dawn's warmth and contracting with evening's cool, creating microcirculations that lift moisture toward the stratosphere, where ozone molecules maintain their protective vigil. The oceans exhale water vapor in quantities that dwarf the most vigorous volcanic outgassing, yet do so with such gentle persistence that the process seems as natural as the tide's retreat. Magnetic field lines thread through the upper atmosphere, invisible guardians that deflect solar particles while allowing the aurora's light to paint the polar sky in colors that echo the first atmospheric chemistry experiments. The trade winds follow their ancient paths across oceanic distances, carrying heat from equatorial regions toward cooler latitudes with the reliability of planetary clockwork. Storm systems form and dissipate within atmospheric layers that maintain their thermal boundaries with remarkable stability, creating weather within the troposphere while leaving the stratosphere undisturbed in its slow circulation. The atmospheric giants rest in their established patterns, supporting the sky through forces so fundamental that they seem as permanent as the planet itself. Time moves differently now in these atmospheric rhythms. Seconds become seasons, minutes become millennia. The patient circulation that began when the first mountains learned to channel air currents continues its work across temporal scales that encompass both the flutter of leaves in afternoon breezes and the slow drift of continents across oceanic basins. The sky that once struggled to maintain its existence above a molten surface now cradles clouds and carries the songs of migrating birds across continents, its stability so complete that consciousness can emerge and contemplate the atmospheric giants that made such contemplation possible. In the quietest moments, when the wind stills and atmospheric circulation moves too slowly for human perception, the ancient giants can still be felt in the gentle pressure of air against skin, the subtle warming of morning sunlight, the soft sound of distant thunder echoing across landscapes that remember when such sounds first learned to travel through atmospheric layers. The sky rests now, supported by giants that have found their eternal rhythm, breathing with the planet in cycles that will continue long after all observers have returned to the stone and air from which they came. Sleep well, beneath the dome of ancient giants who learned to hold up the sky.